Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the darkness between the stars, a single light is failing. Once it shone brilliantly, a beacon of warmth in the cosmic night. But now it flickers with a fragile, unsteady glow. The star is dying. For millions of years it burned in a delicate balance, its fierce nuclear heart pushing outward against the relentless inward pull of gravity. It may have warmed planets, illuminated nebulae, and been a sun to some distant world. But nothing in this universe is truly eternal. Now its fuel is nearly gone, and that balance has tipped. Deep inside the star's core, the furnace that sustained it is running out of flame. There is a hush, where once there was the roar of fusion. Gravity, ever patient, tightens its grip, squeezing the core harder and hotter in a desperate last attempt to keep the lights on. The star trembles on the brink. Its outer layers, once held taut by the pressure of light from within, begin to slide inward under gravity's command. If we could hear across the vacuum of space, we might catch a deep, forlorn groan as the star's very structure gives way. In one final, agonizing moment, the core of the star collapses. Ages of stellar life are undone in less than a heartbeat. Matter, that was the star's heart, is suddenly rushing inward at a significant fraction of the speed of light. Atoms are smashed together, nuclei are crushed, and the temperature spikes to unimaginable levels. It's as though an enormous weight has slammed down on the star's core, squeezing it to a fraction of its former size. Then, like a compressed spring uncoiling, all that pent-up energy is released. In that instant, the star that had faded now explodes in a blaze of glory. A flood of energy bursts outward from the core. What was moments ago a dimming ember becomes a sudden supernova, a titanic explosion of light and matter. The star's outer layers, which were collapsing inward, are blasted back out into space. In the span of a single second, a celestial object the size of a sun is torn apart. The darkness of a quiet cosmic night is pierced by a bloom of brilliance. The dying star outshines its entire galaxy, a flare of radiance against the void, like a colossal flower unfolding in fire. Anyone watching from a nearby world would see their night sky ignite with a light greater than 1,000 suns. For a brief time, this supernova shines with ferocious intensity. Gases that once formed the star's flesh are hurled into space as glowing shreds. Petals of stellar material, incandescent hydrogen, helium, and new forged heavier elements expand outward in great filamentary veils. And then, as suddenly as it began, the brilliance starts to fade. The explosion exhausts its initial energy and begins to settle. Where once there was a star, there is now a vast, ghostly cloud expanding through space. In its center, a tiny, fiercely hot remnant may persist, perhaps the collapsed core, transformed into a dense neutron star, or perhaps nothing visible at all if even the core succumbed to an all-consuming collapse. The light of the supernova dims from blinding to merely luminous and continues to wane over weeks and months, until to most eyes the sky returns to its familiar darkness. The star is gone. All that remains is an expanding shell of gas, a nebula glimmering faintly with the last light of the star's dying breath, and, if the star's heart survived, a small, strange object hidden at the center of that nebula. In the silent aftermath, the cosmos is quiet again. Yet in that silence lies not just an ending, but a new beginning written in the ashes. The materials ejected by the star are mixing with the interstellar medium, ready to become part of something new. Every star's death is written by the life that led up to it. To understand this final blaze of glory, to truly grasp why the star had to die and how its death will give rise to new light, we must step back and watch how a star lives. Only then can we appreciate the full story, how a star's life creates the conditions for its death, and how even in dying, a star brings new light to the universe. Eons before that final eruption, our star's story began in darkness, a different kind of darkness, filled with promise. In a cold, dense cloud of gas and dust adrift in the galaxy, something subtle but significant occurred. Perhaps the passing shockwave of an older star's supernova swept through the cloud, or two galaxies brushed past each other and stirred the cosmic dust. Whatever the trigger, a region of the nebula began to condense. Gravity, the same force that would eventually destroy our star, was the midwife at its birth. What began as a diffuse, invisible patch of hydrogen gas slowly gathered into a tighter clump. As the gas particles drew closer together, their mutual gravity grew stronger, pulling in more and more material. The cloud fragmented into pockets. One of these pockets would become our star. Within that shrinking globule of gas, matter rushed inward, and the density and temperature at the core of the clump soared. At first, it was just a protostar, a warm, thick knot of gas still shrouded by the cocoon of dust from which it formed. The newborn protostar did not yet shine with its own light in the visible spectrum, but it was heating up steadily. As it grew in mass, pulling in material from the surrounding nebula, it began to spin faster, much as a dancer spins faster when pulling in their arms. A swirling disk of leftover gas and dust flattened around it. Occasionally, the protostar's growth was so violent that it ejected some material back out along its poles in narrow jets, like cosmic geysers, carving through the surrounding gloom. If we could have seen inside the nebula, we might have observed multiple such protostars forming in a cluster, siblings born from the same cloud, each gathering their own disks. Our protostar, for a time, was just one glowing embryo among many in a stellar nursery. Gravity kept squeezing that protostar's core, tighter and hotter, until one day, after perhaps millions of years of slow compression, the temperature at the center crossed a critical threshold. The star's heart caught fire. Hydrogen atoms, which had been pressed together more and more fiercely, suddenly began to fuse with one another. 4 hydrogen nuclei merged into one helium nucleus, and in that transformation, a tiny fraction of mass converted into a tremendous amount of energy. This was the moment of birth. The protostar's hidden fire ignited into starlight. The cocoon of dust was blasted away by the newborn star's radiance, and it announced itself to the universe as a new sun. The star settled into a long adulthood, blazing contentedly in a steady golden glow, if it was of moderate mass like our sun, or maybe a brilliant blue-white if it was much more massive, or a dim red if it was smaller. Its core became a powerhouse of fusion, turning hydrogen into helium and flooding the interior with energy. That energy pushed outward as light and heat, creating pressure that held up the star's weight. Gravity pulled inward, thermonuclear fire pushed outward. The two forces balanced in a beautiful, stable harmony. Astronomers call this hydrostatic equilibrium, but one might simply think of it as the star's heartbeat, a steady outflow of energy keeping gravity's crush at bay. For the majority of a star's life, this balance persists. Our own sun, for example, has been in this stable phase, the main sequence, for about 4.5 billion years, and will continue similarly for about 5 billion more. During this time, the star changes very little to the casual observer. It shines with a nearly constant brightness, day after day, century after century, its surface seething and churning, but its overall output steady. If the star has planets around it, they bask in this steady glow. Life, as on Earth, might have the chance to arise and evolve under the star's reliable warmth. Yet even a star's life, though long compared to ours, is not truly eternal. The fuel in its core is finite. The larger and hotter the star, the faster it burns through its supply. A truly massive star, dozens of times heavier than the Sun, might exhaust its core hydrogen in only a few million years. an eye blink compared to the Sun's 10 billion year lifespan. A tiny red dwarf star, on the other hand, sipping its fuel frugally, can shine for hundreds of billions of years. But eventually, in every star, the day comes when the hydrogen in the core is mostly spent. The core, now largely helium ash, can no longer sustain the same rate of nuclear burning. The outward pressure begins to falter, and gravity starts to gain the upper hand. The star has reached the end of its youth and stands at the threshold of its first great crisis. The first sign of a star's impending death is a profound transformation. As the core's fusion ebbs, nothing is left to hold up the weight of the star's outer layers. Gravity pushes those layers inward, compressing and heating the core once again. Paradoxically, this new squeeze of gravity provides a temporary lifeline. Around the inert helium core, a shell of hydrogen, which was previously too cool to fuse, now becomes hot enough to ignite. The star gains a second wind. Hydrogen fusion resumes in a shell around the core, pumping out energy furiously. This causes the outer layers of the star to swell outward. The star's radius balloons to many times its former size. As the surface expands, it cools and reddens, much like a piece of metal glows red when cooler but white when very hot. The once steady yellow star becomes a red giant, bloated and luminous, but cooler on its surface, with a heart of helium ash hidden at its center. If this star once had orbiting planets, their fate is precarious. During its expansion, the star's atmosphere reaches outward dramatically. A world that was once comfortably distant may now be inside the star's tenuous outer layers. Mercury and Venus, for instance, will be engulfed when our Sun becomes a red giant. Earth may or may not be swallowed whole. Some calculations suggest Earth might spiral outward due to the Sun's mass loss, just evading direct consumption. But even if it isn't engulfed, it will be scorched beyond recognition. In either case, the inner worlds will be burned and likely destroyed. Imagine for a moment being on a hypothetical moon of a distant gas giant, watching this happen. Over thousands of years, your sun grows ominously larger and redder in the sky. By the end, it spans a huge portion of the heavens, a dim red Goliath casting an eerie copper glow. The heat is relentless. Oceans boil away, atmospheres escape, surfaces melt. The gentle star that nurtured life has transformed into a ruthless juggernaut. Inside the red giant, while the outer layers swell and cool, the core is contracting and heating. When the temperature and pressure in the helium core become high enough, a new kind of fusion begins. Helium nuclei start fusing into carbon and oxygen. For a star like the Sun, this onset of helium fusion can be sudden, a phenomenon called the helium flash, where the core ignites in a runaway burst of energy, though the energy is absorbed and does not blow the star apart. In more massive red giants, helium ignition is a more sedate onset. Either way, the star now has a new fuel. For a while, helium fusion in the core provides an internal energy source, which somewhat stabilizes the star again. The star's radius might shrink slightly, and its surface temperature might increase for a time, especially in stars a bit more massive than the Sun, which forms something called a horizontal branch state. For a period of time, the star finds a bit of equilibrium once more, quietly burning helium to carbon and oxygen in its center. But this reprieve is relatively short-lived on cosmic timescales. A star like the Sun will burn helium in its core for only a few tens of millions of years, a mere flicker compared to the billions of years it spent burning hydrogen. Eventually, the helium too is exhausted, and this time, the star's core is left with carbon and oxygen, elements that for a modest-sized star are effectively inert. The core is not hot enough to fuse them into heavier elements. Fusion grinds to a halt in the center once more. The inert carbon-oxygen core, incredibly dense and hot, continues to contract under gravity. But now something quantum mechanical and strange comes into play. The core's atoms are packed so tightly that the electrons, in effect, refuse to be squeezed any further. They generate a quantum pressure, electron degeneracy pressure, that halts the collapse. The core, perhaps the size of Earth, but with half the Sun's mass, is as compressed as it can get, without triggering further fusion or collapse. Meanwhile, the star's outer layers have become unstable. Without a vigorous energy output from the core, nothing can hold on to those distant layers. In the star's final breaths, it begins to pulsate. With each pulsation, it coughs away great shells of its own gas into space. Gentle stellar winds grow into intense gusts, pushing the star's envelope outward. The red giant sheds its skin, layer by layer. Over some thousands of years, the star loses a significant fraction of its mass this way. What remains at the center is the hot, naked core, now exposed for the first time to the outside universe. The escaping outer layers form an expanding cloud around it. The core is fiercely hot, hundreds of thousands of degrees, and its ultraviolet radiation causes the receding gas to fluoresce. What was once the star's atmosphere now becomes a gorgeous planetary nebula, a glowing shell of multicolored gas stretching out into the void. These nebulae are among the most beautiful objects in astronomy. They take on fantastical shapes, sometimes a nearly spherical bubble, other times a bipolar structure like two facing cones, and often complex rings and halos. To early astronomers with small telescopes, some resembled the round shapes of planets, hence the name planetary nebula, though they have nothing to do with planets. Our dying star's cast-off layers might form a luminous ring or an intricate lace-like web. As the ultraviolet light from the central core floods outward, it excites different elements in the gas. Hydrogen glows red, oxygen glows green-blue, nitrogen can add touches of red as well. The nebula may appear as a haunting turquoise halo, or a delicate rosy sphere embedded with filaments. Some planetary nebulae appear as if a cosmic iris had opened its eye in the depths of space, with the central star as the pupil. These structures are often symmetric and eerily beautiful, expanding at tens of kilometers per second into the surrounding darkness. Such a nebula doesn't last long, a mere few tens of millennia, before dispersing into the wider galaxy. As it expands, its gases cool and dilute, fading from view. One day, not far by cosmic standards, the nebula will merge back into the interstellar medium from which the star once formed. But while it shines, it creates an unforgettable tableau, the farewell gesture of a star like our Sun. At the center of the expanding nebula lies what's left of the star's core, a white dwarf. This object is the smoldering ember of the star, incredibly hot at first but destined only to cool over time. It is a sphere of carbon and oxygen about the size of Earth, but containing roughly half the mass of the Sun. A teaspoon of its material on Earth would weigh tons. Inside this dense core, matter is supported by electron degeneracy pressure. The electrons crowding each other provide the stiffness that prevents further collapse. The white dwarf is initially bluish-white from the immense heat of its exposed interior. With no nuclear fusion to replenish its energy, those fires have gone out forever. It simply radiates away its stored thermal energy into space. Over billions of years it will fade from white to yellow to red, and eventually become utterly dark. At that final stage, it is sometimes called a black dwarf, a cold, inert cinder in which even the residual glow has died out. However, the universe is not yet old enough for any black dwarfs to exist. Our star's white dwarf will shine, albeit weakly, for longer than the current age of the universe before it truly goes black. There is a poetic notion that as a white dwarf cools, its carbon might crystallize like a gigantic diamond. In fact, observations hint that some old massive white dwarfs have partially crystallized interiors. One could imagine that in the far future, the core of our Sun might become a diamond the size of Earth, drifting through the galactic night. For now, Our white dwarf is still extremely hot and luminous in ultraviolet and X-rays, which is what lights up its planetary nebula. Over time it will fade, but during the nebula's brief glorious existence, the white dwarf is a brilliant pinpoint at the center, a cosmic tombstone marking where a star's heart remains. This is the fate that awaits our Sun and other stars of similar mass. A gentle, if somewhat melancholy, end, a final flowering as a nebula, and the quiet retirement of the core as a white dwarf. No spectacular explosion destroys the star outright. Instead, it is a slow shedding of worldly goods, a final display of color and light, then a gradual fading into the night. It is a quieter death than the ferocious supernova we imagined earlier. Yet, from the perspective of the universe, even this mild death has great significance. The outer layers shed into space carry elements that the star forged in its later life, elements like carbon and nitrogen, produced during the red giant phase. These become part of the raw material for future stars and planets. The star's death, though calm, seeds the cosmos just as surely as a supernova does, if in a more modest way. In dying, the star gives back much of its substance to the galaxy. Still, one might ask, what if a star had been born much more massive? Not all stars go gentle into that good night. For those born with significantly more mass, 8, 10, or 20 times the mass of the Sun or more, the final act is far more violent. When a high-mass star exhausts its core hydrogen, it, too, balloons into a supergiant. A red supergiant if relatively cool, or possibly a yellow or blue supergiant depending on its mass and stage. Inside, it goes through a furious sequence of burning stages. Unlike a low-mass star, a massive star can fuse elements beyond helium because its core gets hot enough to ignite heavier and heavier fuel. After helium is used up, creating carbon and oxygen, the core contracts and heats until carbon can fuse, producing neon, magnesium, and other elements. When carbon is depleted, the core, now largely neon and oxygen, contracts and ignites those. Neon fuses to oxygen and magnesium. Oxygen later fuses to silicon and sulfur. Silicon eventually burns to produce iron. The star's interior becomes layered like a giant onion, concentric shells where different fuels are burning. Hydrogen in an outer shell, helium in a shell beneath that, carbon, oxygen, neon, and so on, with an iron core forming at the center. Each successive stage of fusion burns faster than the last. A process that took millions of years for hydrogen and hundreds of thousands for helium takes mere centuries for carbon, then only years for neon, months for oxygen, and perhaps days or even mere hours for the final burning of silicon into iron. The reason is that as the star steps up the ladder of elements, the efficiency of energy production drops, so it has to burn through the fuel much faster to sustain itself. Finally, the star's core is composed of iron and nickel nuclei. And here the chain of fusion terminates, because iron is a dead end in terms of energy. Fusing iron into heavier elements does not release energy. It actually consumes energy. The star has no more nuclear fuel that can produce an outward push. The iron core grows to a critical mass, about 1.4 times the mass of the Sun, though compacted into a sphere only perhaps the size of Earth. At that critical point, the core can no longer support the tremendous weight of the star's envelope pressing down on it. In less time than the blink of an eye, the core collapses. Gravity wins decisively, catastrophically. The core's atoms are crushed together so forcefully that electrons are shoved into protons, turning them into neutrons and neutrinos. The entire core, which moments before was the size of a small planet, implodes to a sphere perhaps only a couple of dozen kilometers across, like a city-sized ball of neutrons. This collapse happens with incredible speed, less than a second. The infalling material reaches densities similar to an atomic nucleus. It's as if an object the size of the Earth suddenly became the size of a city. The violence of it is difficult to imagine. The collapse is eventually halted by the hard core of neutrons. Think of it like a rubber ball hitting a wall. The core bounces a little, sending a shock wave outward. At the same time, in that brief moment of formation, the new neutron core releases an immense burst of neutrinos. These ghostly subatomic particles rarely interact with matter, but so many are produced, carrying off about 99% of the collapse energy, that they impart a shock to the overlying stellar material. The combination of the rebound and the neutrino blast causes the star's infalling layers to explode outward. The result is a titanic supernova explosion, the same kind of event we described at the beginning. The outer parts of the star, by now expanded into a supergiant, are blown off in a tremendous blast, racing into space at a significant fraction of the speed of light. The energy released is almost unimaginable. For a brief period, the exploding star can radiate more energy than all the billions of other stars in its galaxy combined. If such a supernova occurred within a few dozen light-years of Earth, it could disastrously affect our biosphere. Fortunately, no star currently that close is poised to explode in this way. The nearest candidate, Betelgeuse, is about 600 light-years away. But even at thousands of light-years, a supernova can be visible to the naked eye. Historical records around the world tell of new stars appearing in the sky. These were supernovae in our own galaxy. In 1054, observers in East Asia, and possibly North America, according to some petroglyph interpretations, recorded a brilliant star in the daytime sky. Unknown to them, they were witnessing a supernova whose remnant is the Crab Nebula. In 1604, astronomers observed another bright supernova, later called Kepler's supernova. Those events were in our Milky Way. Supernovae in nearby galaxies have also been visible to the naked eye, such as one observed in 1987. If Betelgeuse were to explode, future generations would see a star as bright as the moon for weeks on end, a celestial beacon announcing the death of a supergiant. As the star explodes, profound things happen inside the blast. The high temperatures and rapid changes trigger nuclear reactions that create new elements. All the elements heavier than iron that the star couldn't produce during its life are now synthesized in the furnace of the explosion. Gold, for example, and iodine, uranium, and many others are forged in seconds by rapid neutron capture and other processes. These precious metals and heavy elements are incorporated into the ejected gas that races outward. The debris of the star enriches the surrounding space with a myriad of elements that did not exist in such abundance before. And what of the star's core? After the supernova, if the core's mass is below a certain threshold, around 1.5 to 2 times the Sun's mass, it stabilizes as a neutron star, a city-sized, ultra-dense object made mostly of neutrons. If the core is above that threshold, for very massive stars, not even the neutron pressure can hold it up, and it continues to collapse into a black hole, a region of space-time with gravity so strong that not even light can escape. Thus, the ultimate fate of the core is decided by the star's mass, neutron star or black hole. In either case, neutron star or black hole, something astonishing remains where the heart of the star once was. Meanwhile, the rest of the star has been blasted into space, forming a supernova remnant that will expand and fade over thousands of years. A core collapse supernova is one of the most magnificent events in nature, the violent death of a massive star. It is an ending on a grand scale, sudden, forceful, and final. And yet, in that destruction lies a kind of creation. The supernova scatters heavy elements that will someday become part of new stars, new planets, perhaps new living beings. Without such supernovae, the universe would lack most of the complex atoms that make up planets and life. So, the star's death, though a dramatic annihilation, is far from pointless. It is, in a sense, sacrificial, a star giving back to the cosmos all the elements it forged in life, and even creating new ones in death. fertilizing the galactic fields for the generations to come. Now let us consider this elemental alchemy more broadly. How, over the history of the universe, stars have served as the forges of the elements. From the hearts of living stars to the violence of their deaths, the chemical elements that compose our world and our bodies have been built up. In addition to hydrogen and some helium, which came from the Big Bang, all other naturally occurring elements were synthesized by stars. Stars in their long, stable lifetimes fuse lighter elements into heavier ones. In their cores, hydrogen becomes helium. When hydrogen is exhausted, helium fuses into carbon and oxygen. Later, in massive stars, carbon may fuse into neon and magnesium, oxygen into silicon, and silicon into iron. These processes happen over millions of years inside stars and produce most of the elements up to iron on the periodic table. The next time you glance at a periodic table, know that each element there has a cosmic pedigree: carbon, oxygen, nitrogen. These were made in star cores. Elements like silicon and sulfur in supergiant stars. Iron, produced in the last gasp of a massive star's life. What about elements heavier than iron, such as gold, lead, platinum, or uranium? These require special, extremely energetic conditions to form. Many are created during supernova explosions, when the flood of neutrons and the intense energy allow atomic nuclei to capture neutrons rapidly and build up into heavy elements, a process called the R process. Still others, especially some of the heaviest like gold and platinum, are now thought to be primarily forged in the colossal explosions that occur when two neutron stars collide. We'll talk about those later. There are also slower processes in aging giant stars, the S process, that builds certain heavy elements over longer periods and gently disperse them via stellar winds. But in general, the universe's inventory of elements beyond iron has been greatly enhanced by violent deaths, supernovae, and neutron star mergers. Consider some examples of this cosmic alchemy. The iron in your blood's hemoglobin was forged in the core collapse of a massive star long before the Earth formed. The oxygen you breathe was cooked in the core of an ancient star and later scattered into space by a stellar wind or explosion. The calcium in your bones was built up in a giant star and cast off in its old age. Carbon, the backbone of life's chemistry, was created by the triple alpha fusion of helium in the core of a red giant star. Even rare elements like iodine, essential to biology in trace amounts, or gold, treasured and malleable, have origins in stellar cataclysms. Iodine likely in supernovae, and gold in the mergers of neutron stars that send debris rich in precious metals into space. Every atom of every element heavier than hydrogen that we find on Earth and in our bodies has traveled through a star. We are, quite literally, made of stardust. The very first generation of stars in the universe, billions of years ago, soon after the Big Bang, had only hydrogen and helium to work with. They forged the first heavy elements and spread them around via supernovae. Subsequent generations of stars were born from gas clouds already seeded with those heavier elements, which meant those stars could produce even more complex elements when their turn came. Over cosmic time, each cycle of star birth and death has enriched the galaxies further. By the time our solar system formed about 4.6 billion years ago, the gas and dust from which the sun and planets condensed were laced with the output of countless prior star deaths. That is why Earth has a crust rich in silicon and iron, why we have water, oxygen plus hydrogen, why there is phosphorus and potassium and all the rest, because the materials had been pre-cooked in stellar furnaces. It's an astonishing connection. The existence of our planet and of us living beings is directly tied to stars that died before the sun was born. We think of those stars as long dead and gone, and they are. But their chemical gifts live on in everything we see around us. In a sense, those ancient stars are not truly gone, because we remember them with every breath and every bite of food. Our very bodies, are their memorial. We truly are made of star stuff. This isn't just a romantic notion, but a physical fact. The atoms that compose our bodies were assembled in stellar cores and distributed by stellar winds and explosions across the galaxy, later to clump and form new worlds and living creatures. The death of stars is intimately tied to the creation of the ingredients of life. Every death, in this cosmic sense, is a kind of rebirth elsewhere. A star once existed for billions of years and then perished, returning its substance to the universe in a moment. And from that substance, new life eventually emerged. It's humbling and ennobling all at once. We are the universe's way of recycling stellar material into consciousness. In dying, stars both destroy and create. They leave behind remnants, like white dwarfs or neutron stars, and scatter their enriched guts across space. Yet not everything of the star is lost in this process. Even as a supernova strews a star's outer layers across the galaxy, the core of the star often survives in a drastically altered form. From the wreckage emerges a stellar remnant that challenges our understanding, an object so dense and extreme that it's like nothing else in the universe. Now, we turn to one such remnant, the neutron star, to witness what becomes of a massive star's heart after the explosive fury of a supernova. Imagine a ball of matter roughly 20 kilometers, 12 miles, across, about the size of a city. Now imagine that this tiny sphere contains more mass than 1.5 suns. This is a neutron star. It's essentially the collapsed core of a massive star, compressed so much that atoms can no longer remain atoms. The crushing gravity forces electrons and protons to combine into neutrons, hence the name neutron star. The entire object is basically a single giant atomic nucleus, an enormous clump of neutrons packed together with incredible density. A neutron star's density defies common sense. A teaspoon of neutron star material would weigh billions of tons on Earth, roughly the mass of a mountain crammed into a spoon. The surface gravity of a neutron star is similarly mind-boggling, hundreds of billions of times stronger than Earth's. If you were to drop a pebble from a height of 1 meter above a neutron star's surface, it would hit the surface in a microsecond and release as much energy as a large bomb. Standing on such an object, if one could, is an impossibility. You would be flattened thinner than a sheet of paper by the gravity. Everything about neutron stars is extreme. The gravity not only crushes matter, it also warps space and time around the star. Light leaving the surface is redshifted, reduced in energy, by the struggle against gravity's pull. If you observed a neutron star up close, its intense gravity would act like a lens, bending the path of light. You could actually see parts of the far side of the star as bent light curving around it. Neutron stars also spin, often at astonishing speeds. The core of the star that became the neutron star was rotating, and as it collapsed, it conserved angular momentum, like a spinning ice skater pulling in their arms. What was a rotation of maybe 1 revolution per day can become 1 revolution per millisecond. Indeed, many neutron stars spin tens or hundreds of times per second. The fastest known spins around 716 times a second. These rapid rotators are called pulsars when they emit detectable beams of radiation. A neutron star typically has a strong magnetic field, inherited and amplified from the star's original magnetic field as it collapsed. If the magnetic axis is not aligned with the spin axis, the rotating magnetic field accelerates charged particles and produces beams of radio waves, and sometimes X-rays or gamma rays, that shoot out along the magnetic poles. As the star spins, these beams sweep around like cosmic lighthouses. An observer in the path of the beams will see the star pulsing on and off, hence the name pulsar. The first pulsars were discovered as very regular radio pulses, so precise that at first astronomers half-jokingly dubbed them LGM for little green men. thinking perhaps they were signals from an intelligent civilization. We now know they are one of the natural marvels of neutron stars. The magnetic fields of neutron stars can be unimaginably strong. The most magnetic ones, called magnetars, have fields about 1 trillion times stronger than Earth's magnetic field. Such a field can distort the electron clouds of atoms from thousands of kilometers away and would erase a credit card on Earth from a distance halfway to the moon. If you somehow approached a magnetar, the magnetic forces would not only scramble your compass, they would disrupt the very molecular bonds in your body. Magnetars occasionally experience starquakes. Their intense magnetic fields put so much stress on the solid crust of the neutron star that it fractures. When a magnetar's crust cracks, the reconfiguration of the magnetic field can release a burst of high-energy radiation. In 2004, a magnetar on the other side of our galaxy erupted and bathed Earth in gamma rays. For a fraction of a second, that single neutron star flare outshone all the stars in the Milky Way. Neutron stars may be small, but they are powerhouses of strange and violent phenomena. Though a neutron star has no more fusion and is technically a dead star, it is far from inert. It begins its life immensely hot, trillions of degrees right after formation, cooling to millions of degrees fairly soon. It emits thermal radiation, mainly X-rays when young, and will take millions of years to cool to more normal temperatures. As mentioned, many emit beams as pulsars. They gradually slow down as they radiate energy. Over very long times, an isolated neutron star will cool and its pulses will weaken, making it harder to detect. These become so-called quiet neutron stars, basically cosmic cinders a few dozen kilometers wide. But even then, if such a collapsed star encountered another star or gas cloud, it could spring into action again by accreting matter and flaring up in X-rays. Neutron stars are like celestial tombs. They contain within them the remnants of a star's core, all its complexity crushed into a hyperdense state. They challenge our understanding of physics, matter on the verge of collapsing into a black hole. In fact, if you were to add just a bit more mass to a typical neutron star, piling on a few more tenths of a sun's worth, you could force it to collapse further into a black hole. They are right on the knife's edge, between existence and oblivion, and this makes them fascinating waypoints in the story of stellar death. They are not the absolute end, but a transformed state of matter, a stepping stone toward the most extreme phenomenon of all. Even more extreme than a neutron star is the fate of the most massive stellar cores, the birth of a black hole. If a stellar core has more than about 2.5 to 3 solar masses after a supernova, gravity overwhelms all possible forces that might hold the core up. The neutrons in a neutron star, which normally resist further compression, themselves succumb if the mass is too great. There is no known force in the universe that can support such a massive core against collapse, so collapse it does, all the way, effectively, to a point of infinite density, a singularity in theory. A black hole is an object, or rather a region of space-time, formed by this total collapse. Around the collapsing core, a boundary forms called the event horizon. This is not a physical surface, but a spherical region of space around the singularity where gravity's pull is so strong that escape velocity exceeds the speed of light. Anything, including light, that comes within this horizon is trapped and inevitably drawn into the center. From the outside, the event horizon is the point of no return. It's as if the core has punched a hole in the fabric of the universe and disappeared. All that's left is an intensely gravitational presence. A black hole that comes from a star might contain a mass of, say, 5 or 10 suns, but the event horizon radius would be only on the order of a few tens of kilometers. For comparison, Earth's radius is about 6,400 kilometers. Imagine an object 10 times more massive than the Sun, crammed into a sphere the size of a small city. That is the scale of a stellar black hole. At the event horizon, not even light can escape, so by definition, the black hole is perfectly black. If you were viewing a black hole from a safe distance against a field of stars, you might notice a strange warping or bending of the background starfield as their light detours around the black hole's gravity. But otherwise, you'd see only blackness in the region of the hole, hence the name. What happens if something, say, an unlucky spaceship or star, gets too close to a black hole? Tidal forces become extreme. Much like the moon causes ocean tides on Earth by pulling a bit differently on the near side versus the far side, a black hole's gravity can vary tremendously over short distances. For a small black hole, for instance, the gravity at a distance of, say, 1,000 kilometers from its center might be millions of times stronger than the gravity 1,100 kilometers out. That difference would stretch any infalling object into a long, thin shape. Scientists grimly term this process spaghettification. A person falling feet first toward the black hole would feel their legs being pulled much more strongly than their head, and the result would not be survivable, to put it mildly. For larger black holes, like those at galactic centers, the tidal forces at the horizon might be less drastic, and one might actually cross the event horizon seemingly unharmed. But as one continued inward, the increasing gravity gradient would ultimately spaghettify and crush any object long before reaching the central singularity. Black holes also distort time. To a distant observer, a clock carried by something falling into a black hole would tick slower and slower as it neared the event horizon, and it would appear to stop entirely at the horizon. In fact, the falling object itself would never be seen to actually pass through the horizon. It would just fade and redden and freeze at the edge from the distant observer's perspective. But from the point of view of the infalling object, or person, there is no abrupt sensation at the horizon. One could cross it without fanfare, aside from those tides, and only later realize there is truly no way out. Inside, all paths lead inevitably to the center, the singularity, in a very short amount of proper time. Because no information can escape from inside the event horizon, what lies at the singularity remains one of the great mysteries of physics. Our current theories break down under those conditions of infinite density. It's possible that, in the real universe, singularities might be smoothed out by some quantum effect we don't yet understand, or perhaps they might even connect to other regions of space-time as speculative wormholes. But as far as observations are concerned, a black hole's interior is beyond our reach. From the outside, however, black holes do have measurable properties: mass, spin, and electric charge, though astrophysical black holes are typically uncharged. Many stellar black holes spin rapidly because the star's core had rotation, and that angular momentum is preserved. A rotating black hole drags space-time around with it, an effect called frame dragging. It can also power jets of high-speed particles if it's actively accreting gas. The rotational energy and magnetic fields can push some infalling plasma out along the poles. In binary systems, a black hole can tear matter from a companion star. That matter swirls into an accretion disk around the black hole, heating to millions of degrees and emitting X-rays and even gamma rays. Such systems are often detectable as bright X-ray sources. In fact, the first black holes were discovered because of their X-ray emissions in binary systems, like Cygnus X1, which alerted astronomers to a likely black hole siphoning gas from an unlucky companion star. It's ironic. A black hole itself emits no light, yet if it has a companion star or gas falling in, it can be among the brightest objects in the sky due to the energetic fireworks of that accretion. If isolated, a black hole is far harder to detect. It essentially becomes a patch of darkness. It can betray its presence only by gravitational effects, like bending light from background stars or influencing the orbits of nearby objects. In recent years, scientists managed to image the surroundings of a black hole directly. A global network of radio telescopes acting in unison, the Event Horizon Telescope project, captured the telltale silhouette of a supermassive black hole in a distant galaxy, seen as a dark shadow against a swirl of glowing gas. For stellar mass black holes, we have not imaged any directly, but their existence is strongly inferred by many observations. Black holes, especially those left by stars, are often quiet passengers in the galaxy. Astronomers estimate there are millions of them drifting through the Milky Way, remnants of ancient massive stars, essentially invisible unless they happen to interact with something. Indeed, one such dark wanderer was recently detected when its gravity magnified the light of a more distant star in an effect called gravitational microlensing, an exceedingly rare and fleeting event that nonetheless gave us a glimpse of an otherwise invisible rogue black hole passing through the galactic neighborhood. In the end, a black hole is perhaps the strangest legacy a star can leave. The star's entire identity, its thermonuclear brilliance, its shining surface, its complex layers, are all erased, collapsed into an infinitesimal mystery. What remains is pure gravity, a warp in space-time, a trap from which nothing can return. And yet, even this is part of the life cycle of the cosmos. Black holes are not malevolent. They are simply another possible end state of stellar evolution. They even play a role in the ecosystem of the galaxy, stirring interstellar gas with their gravity and merging with each other to release new kinds of energy in the form of gravitational waves. Thus far, we have explored what happens to individual stars at the ends of their lives, planetary nebulae and white dwarfs for the smaller ones, supernovae with neutron stars, or black holes for the larger ones. But the story does not end with these remnants. These stellar ghosts, the white dwarfs, neutron stars, and black holes left behind, continue to drift through the galaxy, and though they are no longer active nuclear furnaces, they are far from irrelevant. In fact, our Milky Way is populated by billions of such remnants, and they quietly influence the evolution of the galaxy. For every star that currently shines in the night sky, there are many faded stellar corpses lurking invisibly in the dark. Imagine the Milky Way not just as a glittering river of light, but also as a vast graveyard of expired stars. White dwarfs, in particular, are extremely common. Practically every low to medium mass star that ever lived in the past 13 billion years of our galaxy's history is now a white dwarf, unless it had a companion and went supernova as a type Ia, which is less common. It's estimated there are many billions of white dwarfs in our galaxy, slowly cooling. Similarly, neutron stars populate the Milky Way in their hundreds of millions, a number gleaned from the vast number of supernovae that must have occurred over cosmic time. And black holes of stellar mass might number in the tens of millions, roaming quietly. These objects are hard to detect when they're isolated, but they are there. Their collective gravitational influence contributes to the mass of the galaxy, some of the missing mass that isn't in visible stars or gas. These stellar remnants are like ghosts, invisible to normal sight, since a white dwarf is very dim compared to a star. A neutron star, often only detectable as a pulsar or X-ray source, and a black hole completely dark unless feeding. Yet, though ghostly, they still have physical effects. A white dwarf, for example, retains most of its star's mass. If it has planets or a companion star, it still exerts a gravitational pull on them. Neutron stars and black holes gravitationally tug on nearby stars if any pass too close, possibly altering orbits over millennia. In aggregate, the population of stellar remnants adds to the galaxy's mass distribution, subtly affecting the motions of stars and gas on large scales. Some stellar ghosts actively announce themselves under the right circumstances. A neutron star with a strong magnetic field spinning as a pulsar will beam radio waves into space. If Earth lies in the path of those beams, we detect a precise periodic signal, a cosmic lighthouse blinking across the void. The pulsar at the heart of the Crab Nebula, the remnant of the 1054 supernova, still powers that nebula with a wind of particles and electromagnetic fields, causing the nebula to glow in X-rays and optical light. Neutron stars can also wander through the galaxy at high speeds. Some are given a kick at birth by asymmetries in the supernova, A fast-moving neutron star plowing through interstellar gas can create bow shocks, like the shockwave in front of a speeding boat, compressing and heating the gas, leaving a trail that could one day seed new stars. Black holes, too, can make their presence known if they encounter matter. In a binary system, as mentioned, a black hole can steal gas from a companion star. That gas, swirling into the black hole, gets intensely hot and radiates X-rays. From Earth, we see such systems as bright X-ray sources. Sometimes the inflow isn't steady. Imagine the black hole biting off more than it can swallow, which can lead to spectacular X-ray flares or even jets of plasma being ejected at near light speed from the vicinity of the black hole's event horizon. We've observed such phenomena in so-called microquasars, stellar mass black holes, mimicking on a smaller scale the behavior of supermassive black holes in galactic centers. Even an isolated black hole might reveal itself by lensing the light of background stars, as mentioned, or by faintly glowing due to the accretion of diffuse gas in the interstellar medium. The combined effect of countless stellar remnants also contributes to the cosmic rays permeating our galaxy. Supernova remnants accelerate particles, protons, nuclei, electrons, to high energies. Many of those particles wander the galaxy as cosmic rays, eventually running into things like our atmosphere, where they create showers of secondary particles. Neutron stars, especially pulsars and magnetars, and black hole accretion disks, can also accelerate particles. These cosmic rays can alter the chemistry in interstellar clouds, catalyzing certain reactions, and may even affect planetary atmospheres over time. Even white dwarfs, the most silently fading of stellar ghosts, can have a later chapter under the right conditions. If a white dwarf is in a close orbit with another star, it can siphon gas off its companion. That gas can accumulate on the white dwarf's surface and episodically ignite in a burst of fusion, causing a nova, a sudden brightening of the white dwarf star system. The white dwarf remains intact, and the process can repeat, essentially a ghost star showing flashes of life by stealing from its neighbor. If the white dwarf accumulates enough mass from its companion to approach the Chandrasekhar limit, 1.4 solar masses, it could even detonate entirely as a Type Ia supernova, obliterating the white dwarf in the process. In that sense, even a dead star can, given the right circumstance, die a second death, taking part in one of the universe's grand explosions. Our galaxy's center houses the largest ghost of all, a supermassive black hole millions of times the mass of the Sun. While not a product of a single star's death, it's the result of many mergers and accretion events over the galaxy's history. It stands as an ultimate example of what gravitational collapse can lead to. This behemoth, lurking about 26,000 light-years from us, in the direction of Sagittarius, orchestrates the orbits of stars in the galactic core. Usually it's quiet, but occasionally it snags a passing star or cloud, producing energetic flares. It reminds us that even at the grandest scale, the remnants of cosmic evolution continue to shape their surroundings. Time is a key factor in how prominent these ghosts are. As millennia and millions of years pass, stellar remnants will increase in number. We live in an era when many stars are still in their shining prime, but far in the future, these remnants will far outnumber the bright stars. The galaxy will eventually become a darker place populated mostly by cooled white dwarfs, dim neutron stars, and black holes, plus diffuse gas. The living, burning stars will be few. In that distant epoch, the ghosts will truly dominate the scene. For now, though, they coexist with a vibrant stellar population. They are like an unseen foundation beneath the more obvious architecture of bright stars. They quietly contribute to the cycle of matter and energy. They provide stepping stones to further cosmic events, like neutron star mergers producing new phenomena. The story of stellar death doesn't end with the initial death. It continues as these ghosts interact, decay further, or sometimes combine in spectacular ways. We've touched on a few hints of even more dramatic events when these stellar remnants meet or interact. Indeed, some of the most breathtaking phenomena in the universe occur when death begets death, when two stellar corpses engage in a final dance or collision. Not all stellar deaths occur in isolation. Many stars are born in binary systems, and their fates are intertwined. Let's explore how binary relationships can lead to unique kinds of stellar demise, cataclysmic variables like novas, the exceedingly bright Type Ia supernovae, neutron star collisions that create gold and gravitational fireworks, and other cosmic pas de deux that enrich the drama of stellar death. Consider a binary star system where one star dies before the other. For instance, imagine a sun-like star and a slightly more massive companion orbiting each other. The more massive star evolves faster, becomes a red giant, and eventually sheds its outer layers, ending up as a white dwarf, while its companion is still in a relatively normal state, perhaps a main sequence star or a red giant of its own later on. Now you have a white dwarf and a second star in a binary. The white dwarf is a tiny, dense object with powerful gravity, and if the two are close enough, it can begin pulling gas away from its still-living companion. The unfortunate companion's star finds its outer layers being siphoned off, spiraling onto the white dwarf. This transfer of mass at first might be a gentle stream, invisibly making the white dwarf more massive. But as the stolen hydrogen from the companion accumulates on the white dwarf's surface, it grows denser and hotter until, flash, the layer of gas ignites in a runaway fusion reaction. In a matter of seconds or minutes, the accumulated hydrogen burns explosively into helium. The white dwarf's surface blasts off a shell of fusion ash into space. From afar, this system suddenly appears to brighten enormously. What was a faint star may become visible to the naked eye as a new star in the sky for a few weeks. This is a nova, Latin for new star. It's not the birth of a star, of course, but rather a flash from a dead star reigniting stolen fuel. In a nova, the white dwarf survives the explosion. It's akin to a stellar hiccup, however energetic. After the blast, the white dwarf can go back to quietly accreting matter from its companion, and after some years or decades or millennia, it might erupt again. Some systems are known as recurrent novae because they flare multiple times. The cycle can continue as long as there's a supply of fresh fuel from the companion, and as long as the white dwarf's gravity can pull material in a stable manner. These nova explosions, while dramatic, are relatively small on the cosmic scale. They don't destroy the star and are minuscule compared to supernova. However, under certain circumstances, a white dwarf in a binary can undergo a far more devastating event. If the white dwarf accretes enough mass from its companion, pushing its mass closer to that Chandrasekhar limit, 1.4 solar masses, the pressure and temperature in its core can become high enough to ignite carbon fusion in an uncontrolled way. Remember, this is a white dwarf made of carbon and oxygen. Unlike hydrogen or helium, when carbon in a degenerate white dwarf core ignites, the burning doesn't gently expand the star to regulate the temperature, because the white dwarf's pressure is supported by quantum degeneracy rather than thermal pressure. An increase in temperature doesn't lead to expansion and cooling. The result is a runaway thermonuclear reaction consuming the entire white dwarf within seconds. The white dwarf detonates completely in one of the most brilliant pyrotechnics the cosmos offers, a Type Ia supernova. In a Type Ia supernova, a tiny Earth-sized object, the white dwarf, is obliterated, unleashing a titanic amount of energy and forging elements like iron, nickel, and cobalt in vast quantities. There is no compact remnant left. No neutron star or black hole remains, because the entire white dwarf is now an expanding cloud of glowing debris. Type Ia supernovae shine with such consistent peak luminosity, about 5 billion times the luminosity of the Sun, that astronomers use them as standard candles to measure distances across the universe. They are cosmologically important, Observations of distant Type Ia supernovae revealed the accelerating expansion of the universe attributed to dark energy. But on a personal level, they are another way that stars die with a creative flourish. They spread iron and other intermediate weight elements far and wide, elements that may not be as abundant in core collapse supernovae of massive stars. So in binary systems with white dwarfs, we have a spectrum, from gentle novae to total annihilation in Type Ia supernovae, depending on how much mass the white dwarf steals and how quickly. Now consider binaries where both stars are massive enough to form neutron stars or black holes. There are binary systems where one star explodes as a supernova and becomes a neutron star, but the two remain bound or become bound again if the kick isn't too strong. Eventually, the second star also goes supernova, possibly leaving two neutron stars orbiting each other, or a neutron star and a black hole, or two black holes. These pairs of dense remnants are essentially ticking time bombs. They spiral toward each other over very long periods as they radiate gravitational waves, ripples in space-time that carry energy away from the orbit. When two neutron stars finally collide, the event is cataclysmic on a different level. Picture two city-sized, insanely dense objects whipping around each other hundreds of times per second as they draw closer. In their last moments, they approach nearly a significant fraction of light speed. When they merge, enormous gravitational and nuclear forces come into play. The merged object can promptly collapse into a black hole, or, if enough support exists briefly, form a hypermassive neutron star for a short time before that too collapses. In the process, a huge mass of neutron-rich material gets flung out into space from the violently merging stars. This debris, rich in heavy elements, heats up and produces an ephemeral but brilliant glow known as a kilonova, so called because it's roughly 1,000 times brighter than a typical nova, though still dimmer than a supernova. The kilonova initially shines blue-hot from freshly synthesized radioactive elements. Then, as those nuclei decay, the glow becomes redder over days and weeks. It was by observing the light from such a kilonova, accompanying a gravitational wave event in 2017, that scientists confirmed that neutron star mergers manufacture heavy elements like gold, platinum, and rare earth elements in significant quantities. The very gold in jewelry here on Earth likely came from such an event in our galaxy's past. The neutron star merger also emits a burst of high-energy gamma rays, a short gamma ray burst, especially if jets form during the collision. These gamma ray bursts are some of the most luminous events in the universe, though very brief, lasting less than 2 seconds for the short variety, longer for collapsor-related bursts. If instead two black holes collide, imagine two invisible dark spheres merging. They release a purely gravitational scream, a burst of gravitational waves, as the only directly observable output. This was what LIGO detected in 2015. The final moments of two black holes merging, converting a few solar masses worth of energy into vibrations of space-time that stretched and squeezed the detectors on Earth ever so faintly. Such events were predicted by Einstein's general relativity and are now observed. They too are endpoints of binary evolution, two stellar mass black holes in a death spiral. There are other exotic binary interactions. A neutron star and a black hole could merge, likely gobbling the neutron star and producing gravitational waves and maybe a faint gamma burst. A neutron star and a white dwarf could collide under rare circumstances, or a black hole could slowly consume a white dwarf or neutron star, tidally shredding it. These scenarios are less commonly observed, but are theoretically possible in dense environments like star clusters. One more comparatively common binary death process. Classical novae we already discussed involve a white dwarf, but there's also a kind of middle ground event called a red nova, or luminous red nova, which occurs when two normal stars merge. While not as energetic as a supernova, it's a stellar death of sorts. The two stars cease to exist as individuals, and become one star. These events can produce a significant outburst, as seen in objects like V1909 Scorpii or others, where contact binary stars spiraled together. The result is a single larger star, often shrouded in dust, and the process may eject a significant amount of the star's mass. It's a death in the sense that two separate stellar lives ended and a new one began. In all these binary cases, what's striking is how the presence of a partner star alters the outcome. A star alone might quietly become a white dwarf and sit there forever, but with a companion, it might reignite and explode. Two neutron stars alone drift through space. Together, they can create one of the most important sources of heavy elements and brilliant fireworks. From the gentle recurring nova that might just create some exotic isotopes and pretty displays, to the awesome Type Ia supernova that serves as a cosmic yardstick and forge of iron, to the mind-bending mergers of neutron stars and black holes that literally shake the fabric of space-time, binary interactions significantly enrich the tapestry of stellar death. They show that even in death, stars are not solitary actors. They can affect one another, sometimes saving their grandest drama for when they are together. Up to now, we have been describing what happens to stars and their remnants more or less from a theoretical perspective. But how do we know all this? Much of the science of stellar evolution and death has been pieced together by observing countless stars at different stages and by physics calculations that have been tested in various conditions. Still, one might wonder, no human has watched a star go through its entire life cycle. It takes millions to billions of years. So how can we be confident in this story? The answer lies in the incredible detective work of astronomy, using both light and other cosmic messengers to understand these processes. Humans have actually observed the deaths of stars for millennia, even if they didn't know what they were seeing. Ancient peoples recorded sudden appearances of bright stars that weren't there before, what we now recognize as supernovae or novae. They regarded them with wonder, sometimes as omens or messages from the heavens. For instance, in July of 1054, observers in East Asia noted a guest star near the star Zeta Tauri. It stayed visible in daylight for weeks. Today, we see the remains of that event as the Crab Nebula in Taurus. Inside it, a pulsar spins, the neutron star left from that massive supernova. In 1604, sky watchers, including the astronomer Johannes Kepler, observed a new star in the constellation Ophiuchus, Kepler's supernova, the most recent known supernova in our Milky Way. These historical accounts, though made without understanding the true nature of the events, are invaluable records. They tell us, for example, that supernovae can occur in our galaxy a few times per millennium. It's likely more have happened obscured by dust or mist due to being in the southern hemisphere, unobserved by Europeans or Far East observers. In modern times, we have developed an arsenal of instruments that allow us to catch stellar death in action across the universe. Telescopes and detectors now cover the electromagnetic spectrum from radio waves to gamma rays, and even beyond electromagnetic signals. We have neutrino observatories and gravitational wave detectors. When a massive star explodes in a galaxy millions of light years away, our optical telescopes see a pinpoint of light that wasn't there before. Robotic telescope surveys scan the sky nightly and automatically flag such new points of light or unusually brightening points. Professional and amateur astronomers then train their telescopes on them to gather more data. By splitting the light with a spectrograph, we see telltale fingerprints of certain elements, perhaps silicon and sulfur lines expanding at high speed, indicating a Type Ia supernova, or hydrogen lines indicating a Type II, core collapse, supernova. The light curve, the way brightness changes over time, provides clues. A Type Ia supernova has a characteristic rise and gradual fall. A massive star supernova might plateau, or have multiple peaks if complicated by circumstellar material. In fact, by studying many such events, astronomers have subclassified supernovae, type 2P, 2L, IN, IB, IS, etc., which correspond to different ways stars meet their end. Some shed their hydrogen envelopes first, some don't, etc. When a supernova occurs relatively nearby, say in a galaxy in our local group, we can sometimes directly see the debris after the explosion fades. The Hubble Space Telescope and ground-based telescopes have monitored supernova remnants and even the actual positions of supernova events decades later to see the shockwave expansion. For example, supernova 1987A, which occurred in a companion galaxy to our own, the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, in 1987, has been observed continuously for decades. We saw a brightening as the shock hit a pre-existing ring of gas, previously expelled by the star, and we've been waiting for the possible emergence of a neutron star or pulsar within the debris. Only recently have there been hints of it. SN 1987A was a bonanza for learning. It was the closest supernova in centuries and was extensively studied across all wavelengths. Neutrinos are a novel way we confirmed our theories. Those ghostly particles from SN 1987A were actually detected in underground detectors on Earth, Kamiokande in Japan and others, a few hours before the visible light of the explosion reached us. This happened because neutrinos, which scarcely interact with matter, streamed out of the collapsing core immediately, whereas photons were trapped until the shockwave reached the surface of the star. The burst of neutrinos, just 24 of them detected, matched the predictions for a core collapse neutrino signal, providing direct evidence of what was happening deep in the star at the moment of explosion. It was a dramatic confirmation of stellar death physics. We felt the star's core collapse through neutrinos, then saw the star blow apart in light. In the past few years, gravitational wave astronomy has opened another new window. In 2015, the LIGO Observatory listened as two black holes merged, which was our first direct detection of gravitational waves. Then, spectacularly, in August 2017, LIGO and its European cousin Virgo detected a signal that indicated two neutron stars spiraling together. Within seconds, a gamma-ray burst was detected by orbiting satellites. Hours later, telescopes spotted a new transient glow in a galaxy about 130 million light-years away, the kilonova from that merger. Here we had essentially the complete story. Gravitational waves told us two neutron stars collided, gamma rays told us jets formed, and the kilonova's light, with spectra showing gold and other freshly made heavy elements, told us about the material ejected. It was perhaps the most observed astrophysical event in history, with dozens of telescopes joining in. This single event confirmed several theoretical ideas at once: that merging neutron stars produce short gamma-ray bursts and heavy elements. It was like witnessing the birth of elements, gold, platinum, etc., in real time. And it showed the power of combining different cosmic messengers, gravitational waves to pinpoint a cosmic death dance, and electromagnetic waves to witness its aftermath. Even black holes, which emit no light of their own, have become observable through their interactions. Aside from LIGO's detections of merging black holes, which produce only gravitational waves, we have observed stars orbiting our galaxy's central black hole over decades. These stars move in tight, fast ellipses, with one star, called S2, coming as close as 17 light-hours to the black hole, 4 times the distance of Neptune from the Sun, and whipping around at a few % of light speed. By tracking these orbits, astronomers have confirmed the presence and mass of the central supermassive black hole. This achievement, in fact, earned the 2020 Nobel Prize in Physics, and as mentioned, we have even imaged the shadow of a black hole's event horizon for the supermassive black hole in galaxy M87, and very recently our own galaxy's center as well, by using radio telescopes spread across the globe. The image appears as a ring of light emitted by hot gas just outside the horizon, surrounding a dark area, the silhouette of the horizon itself. It's a stunning confirmation that the dark star predicted by general relativity is real. When it comes to observing stellar ghosts, pulsars have been detected by their pulses. Over 2,000 are known to date. Some pulsars are in binary systems, which allows us to test general relativity, such as the famous Hulse-Taylor pulsar, a neutron star pair that spirals inward exactly as gravitational wave emission predicts. White dwarfs have been observed in huge numbers as well, often through surveys like the Sloan Digital Sky Survey. We can even see extremely faint white dwarfs in clusters like M4, giving a hint that some are crystallizing as they cool. These observations line up with the theory that white dwarfs cool and fade over billions of years. Novae are observed fairly frequently in our galaxy. About 10 per year are seen, and many more likely occur on the far side of the galaxy hidden by dust. Each nova gives us insight into the accretion processes on white dwarfs. Some have even been observed to recur, e.g. RS Ophiuchi, which erupts about every 15 to 20 years. Supernova remnants, like the Veil Nebula or Cassiopeia A, have been mapped in detail by telescopes. In Cass A, the remnant of a supernova around 1680 AD, though oddly no one clearly recorded it at the time, astronomers have found the neutron star left behind, and they've even seen light echoes in surrounding dust that give clues to the original explosion. In X-rays, Cass A's image from Chandra shows an incredible expanding shell with different elements separated spatially. For example, iron is more interior, oxygen and magnesium more outside, consistent with our understanding of how supernova nucleosynthesis and ejection work. Our ability to simulate stellar deaths on computers has also advanced. We can now create models that, for example, follow a massive star's collapse and explosion and see how asymmetries can give a neutron star a kick, or how mixing can produce certain light curves. These models are tuned by matching them to observations, say, the light curve of SN 1987A, or the spectra of various supernovae. While some details are still being researched, like the precise mechanism that makes every core collapse supernova explode rather than implode entirely, neutrinos are key, but it's a complex hydrodynamic dance. The broad strokes are strongly supported by data. Thus, through a combination of direct observation across all wavelengths, and now beyond light, historical evidence, laboratory physics, and computational modeling, we've assembled the story of stellar life and death. Each new technological leap, from Galileo's first telescope to spectroscopy, to space telescopes above our atmosphere, to neutrino detectors, to gravitational wave observatories, has added a piece to the puzzle or confirmed a chapter of the tale. We no longer merely speculate about star death, we witness it. We have seen the X-ray glow of neutron stars feeding, the gentle wink of novae, the sky-filling blast of supernovae, the faint whisper of colliding black holes. Even now, somewhere in the universe, a star is living out its final moments. Perhaps in a distant galaxy, a red supergiant's core has just collapsed, neutrinos streaming out, a shockwave on the way. Within the next few hours or days, light from that explosion will start its journey across space. In a few years, maybe it will arrive at Earth, and robotic telescopes will catch a new star in their images. Alerts will go out, astronomers will turn their instruments to study it, and humanity will collectively witness another star's death in as close to real time as nature allows. With every such observation, our understanding deepens. We are, in a sense, collecting the final words of stars, listening to their swan songs, and learning from them. One day, we will face a very personal case of stellar death, that of our own sun. But fortunately, that is far in the future. Our sun is currently a healthy middle-aged star, shining steadily and nurturing a rich biosphere on the third planet from its warmth. Yet, like all stars, it must eventually exhaust its fuel and transform. What will that look like? And what will become of the Earth? Our Sun is about 4.6 billion years old. It's roughly halfway through its main sequence lifetime. For the next few billion years, it will continue to fuse hydrogen into helium in its core, gradually getting hotter and slightly more luminous as the helium ash accumulates. In fact, the Sun's brightness has increased by about 10% since it formed. In another billion years or so, that slow increase will make Earth significantly warmer, potentially too warm for complex life long before the dramatic red giant phase arrives. By around 5 billion years from now, the Sun will have run out of core hydrogen. At that time, it will begin the transition into a red giant. The Sun's core will contract and heat, just as we described earlier, and hydrogen fusion will ignite in a shell around the core, causing the Sun's outer layers to expand tremendously. It's estimated that at its largest, the Sun's radius will extend to somewhere around Earth's orbit. Perhaps a little less, perhaps a little more. The exact calculations are complex and depend on how much mass the Sun loses as a red giant. Mercury and Venus will almost certainly be engulfed and vaporized. Earth's fate is uncertain. Some models suggest Earth will be swallowed by the Sun's expanded atmosphere, dragged inward by tidal interactions, and incinerated. Other models suggest Earth might just barely survive, orbiting within the Sun's outermost tenuous layers, or just outside them after orbital expansion due to the Sun's mass loss. Either way, the Earth's surface will be sterile. Long before the Sun actually touches Earth, the increasing heat will have boiled away the oceans and stripped the atmosphere. The crust will glow red hot. For a while, Earth might resemble a desiccated rock, like Mercury, under the gigantic red orb of the Sun, filling the sky. By the time the Sun is at its largest, even the outer planets will experience vastly increased solar heat. Mars might briefly enjoy Earth-like temperatures, though bathed in red light, but not for long. If any humans, or our far future descendants, are still around by then, they would have had to leave Earth, and perhaps the solar system entirely. Maybe they would take refuge in the outer reaches, on moons of Jupiter or Saturn, which might become temperate for a short period. Or more likely, humanity would undertake voyages to other star systems long before that. It's poignant to imagine that far future observers, perhaps the distant descendants of humanity or some other species that by then knows this story, could watch from a safe distance as the Sun goes through its death throes. They might see the Sun's color turn from yellow-white to orange to deep red as it expands. They would know, as they watch, that this was once the star that sustained the cradle of human civilization. The emotions such observers might feel blend sorrow at the loss of the Sun's former life-giving form and awe at the grandeur of the transformation. As the Sun's core continues to contract, it will eventually ignite helium fusion in a flash, as described earlier. The Sun will shrink slightly and settle into a stable helium-burning phase for a time, becoming perhaps a bit less distended. It might then expand again for an asymptotic giant branch phase after helium is exhausted, undergoing some thermal pulsations, each expelling more of its outer layers. Finally, the Sun will shed its outer envelope. The dying Sun will create a planetary nebula, perhaps a glowing shell of ionized gas expanding outward, beautiful in its complexity. Some models suggest the Sun's planetary nebula might be relatively faint, because the Sun is not as massive as the stars that make the showiest nebulae. But it will still be a sight to behold, a ring or bubble of color, marking where our star says farewell. At the center of that nebula will lie the Sun's core, a fresh white dwarf. It will likely be composed of carbon and oxygen, about half the Sun's present mass, compressed into roughly Earth's volume. It will be extremely hot, well over 100,000 degrees Celsius at the surface initially. It will cool slowly over billions of years. Once the surrounding nebula drifts away into space, the white dwarf Sun will remain, a small, dense, gradually cooling sphere. It will shine mostly in the ultraviolet initially, with perhaps a bluish-white hue if one could see it up close, then fade through the colors to red, and eventually to darkness over trillions of years. The solar system, as we know it, will not survive this process intact. The inner planets will be gone or altered beyond recognition. The gas giants might migrate outward as the sun loses mass, since the gravitational hold will weaken. The icy bodies of the outer solar system, Kuiper belt objects, Oort cloud comets, will largely drift away or get perturbed by the changing gravity. The final configuration might be a white dwarf with a few distant cold planets, perhaps Jupiter, Saturn, Uranus, Neptune, if they aren't lost, now wandering farther out, perhaps some moons or dwarf planets, frozen solid. Over enormous timescales, even those remaining planets might detach or be perturbed by passing stars. It is a sobering scenario, the demise of our warm and life-sustaining sun. Yet, it is also strangely uplifting to know that the sun's materials will not be lost. The planetary nebula cast off by the dying sun will carry atoms that once made up our world out into the galaxy. Perhaps some of those atoms will eventually find their way into new star-forming clouds. In that sense, a piece of Earth and a piece of us will journey on, joining the great cycle of cosmic recycling. In fact, there is a theory that a supernova may have helped trigger the formation of our solar system over 4.6 billion years ago, based on certain isotopes found in meteorites that are byproducts of supernova nucleosynthesis. If true, then a star's death begot the sun's birth. And now we see that the sun's death will return the favor by contributing its matter to future generations of stars. The cosmic cycle continues. Now let's journey unimaginably far into the future of the universe, beyond not just the death of individual stars, but to the era when perhaps all stars have died. What happens after the age of starlight? The universe is about 13.8 billion years old. We live in what astronomers call the stelliferous era, age of stars, when galaxies gleam with billions of active stars. But stars consume fuel. Galaxies have a limited gas supply, and over time, star formation will slow. Astronomers project that star formation will continue on a declining curve for many trillions of years, gradually winding down as gas gets locked into long-lived dwarf stars or compact remnants. The smallest, most long-lived stars, red dwarfs, burn their fuel so slowly they can shine for trillions of years. So there will be stars twinkling for a very long time yet. But eventually, even those miserly red dwarfs will exhaust their hydrogen and turn into inert helium white dwarfs. Let's sketch the timeline. In about 100 billion years, the expansion of the universe, driven by dark energy, will likely have pulled all but our local group of galaxies beyond the observable horizon. Future beings in our galaxy at that time might think the Milky Way is the entire universe, as distant galaxies' light will have redshifted into oblivion. But stars will still be shining in our galaxy then. Fast forward to, say, 1,010,012 years from now. By this time, most stars larger than red dwarfs will have long since died. New star formation will be a trickle. Much of the interstellar medium will have been either locked in remnants or swept out of galaxies. Some star formation might still occur from collisions of brown dwarfs, or stellar remnants occasionally merging and sparking new stars briefly, but on the whole, galaxies will be dimmer. Red dwarfs, whose lifetimes can reach into the trillions of years, will dominate the starlight. They will be faint red glowworms where once splendid suns like ours shone. At around 10 trillion, 10,013 years, star formation will essentially cease. The reserve of gas for making new stars will be effectively depleted or too spread out. The universe's expansion will have put far-flung raw material beyond reach. The existing stars will run out of fuel one by one. The last truly luminous star might be a red dwarf finally flickering out. Imagine that far future night sky. From some hypothetical planet around one of those last stars, if planets still exist. Where once the sky was full of stars, now perhaps only a few faint red points pierce the darkness. Maybe globular clusters remain as isolated pockets of stars, slowly losing members to the galactic halo. The Milky Way,
or whatever merged galaxy exists by then. Our Milky Way might merge with Andromeda and others to form a large elliptical over billions of years. We'll no longer have the majestic spiral arms lit by young stars. It might be a huge ball of dark mass with occasional pinpricks of degenerate matter. When the last active star, likely a tiny red dwarf, finally exhausts its hydrogen, perhaps after 10, 14, or 10, 15 years, 100 trillion to a quadrillion years, it will expand into a small red giant, shed a bit of mass, then fade to a white dwarf. At that point, the degenerate era begins in full. The universe will be populated only by stellar remnants, white dwarfs, many of them cooled to become black dwarfs by then, neutron stars, and black holes, along with unbound planets, brown dwarfs, failed stars, and cold gas and dust. The average temperature of the universe will be dropping as well, as the background radiation is stretched to extremely low energies by expansion. What is life like in such an era? It's speculative whether life could find ways to survive around, say, a warm white dwarf, or on residual heat of a cooling neutron star, or by feeding off rotational energy of pulsars. Some scientists have pondered civilizations around white dwarfs, or even artificial habitats, feeding off black hole accretion disks, since black holes could theoretically provide energy via Hawking radiation or other mechanisms over extremely long timeframes. If any form of intelligence endures into these times, it would face ever-declining energy supplies. Time stretches on. White dwarfs gradually cool toward the background temperature, which itself might approach near absolute zero if dark energy leads to a de-Sitter space. On timescales of 10^19 to 10^20 years, most of the remaining planets will have either spiraled into their remnants due to gravitational radiation or interactions, or been flung out by gravitational encounters. The galaxy's shape will disperse as gravitational interactions over eons cause stars and remnants to scatter, some being ejected into intergalactic space, others falling into the central black holes. Around 10^20 years, 100 quintillion years, the Earth, if somehow it survived as a charred ember around the white dwarf sun, would either have been absorbed by the sun's white dwarf due to orbital decay from emitting gravitational waves, though that timescale is way longer than that for Earth-Sun, or more likely, the sun's white dwarf might have cooled to, say, a few thousand K, glowing faintly red. By 1025 years, definitely, any white dwarf like the sun's will be essentially a black dwarf, radiating at almost the same temperature as the cosmic microwave background, which itself would be incredibly cold then. To any remaining observer, these once stars would be effectively invisible unless you literally bumped into one. Over extremely long timescales, quantum effects might come into play. If protons are unstable, some theories predict a proton's half-life of 1034 years, then given enough time, all the atomic nuclei in white dwarfs, planets, etc., would eventually decay into lighter particles, like positrons and gamma rays. A white dwarf could slowly evaporate into a cloud of electrons, positrons, and radiation. If protons don't decay, another process can still thin out matter. Quantum tunneling could cause the iron in black dwarfs to fuse, or the object to collapse on unimaginably long timescales, 10 or 1500 years or more, or cause it to crystallize fully and just sit. One thing that will definitely happen in the far, far future is the slow evaporation of black holes via Hawking radiation. Black holes aren't completely eternal. Quantum mechanics suggests they emit a very faint trickle of particles and radiation, losing mass in the process. For a stellar mass black hole, the evaporation time is stupendously large, around 10^67 to 10^100 years, depending on mass. For the supermassive black holes, it's even larger, on the order of 10^100 years or more. But given enough time, even these leviathans will evaporate,
each ending its life in a final burst of Hawking radiation that might briefly be as energetic as a small explosion. After that, nothing of them remains. As we approach times like 10 or 100 years and beyond, the universe becomes very quiet and sparse. All galaxies have dissipated. All black holes are gone. The particles left are mostly subatomic: electrons, positrons, neutrinos, and extremely low-energy photons, stretched out to absurdly long wavelengths. The expansion may eventually dilute even those, so that on average, you might have to search a volume larger than the observable universe today to find a single particle. The temperature of the universe will asymptotically approach absolute zero. This is the heat death of the universe, sometimes called the Big Freeze. It's a dark picture, endless space with virtually nothing in it. No starlight, no planets, no warmth, just the feeble afterglow of a cosmos that once blazed with galaxies. If consciousness or life hasn't found some way to circumvent the need for conventional energy, it would have long since flickered out by this stage. This is the ultimate endpoint of all the individual star deaths we've discussed. Everything ends, even the cosmos as we know it. Unless, perhaps this isn't truly the end. Some speculative ideas suggest that given inconceivably long times, random quantum fluctuations could produce a new Big Bang or a Boltzmann brain, a self-aware configuration of particles popping up by chance, though the time frame for that is mind-boggling. Other theories propose that our universe might tunnel into a lower energy vacuum state, essentially triggering a new kind of Big Bang that restarts things, though that would obliterate the current universe in the process. These ideas are currently beyond verification and wander into the realm of metaphysics or highly theoretical physics. For all practical purposes, under known physics, once the last black hole evaporates, the universe will be effectively dead for eternity, an ever-expanding, nearly empty darkness where nothing of note happens. This future is almost impossibly far away. It makes the lifespan of even the longest-lived star seem like a blink, yet thinking about it can evoke a deep sense of existential awe. The universe had a beginning, and it may have an end. We live in a chapter, the chapter of shining stars and bright galaxies, that will not last forever. But it is our chapter, rich with story and meaning. Through this long exploration, a theme has quietly taken shape. In the cosmos, every death is also a form of creation. A star's death creates the chemical elements that may seed life. The remnants of stars lead to new phenomena, pulsars, black holes, that enrich the fabric of reality with their strange properties. Even the eventual fade of the universe sets the stage for who knows what, perhaps a rebirth, perhaps a final piece. Philosophically, the story of stellar death resonates with us because it mirrors aspects of our own existence. We are born, we shine with life, we use up our days, and eventually we must go. But we are part of cycles larger than ourselves, biological cycles, cultural cycles, and indeed cosmic cycles. There is an ancient intuition in many mythologies that destruction and creation are two sides of a coin. From the ashes of the phoenix, a new phoenix arises. In Hindu mythology, the dance of Shiva destroys so that Brahma may create anew. The ancient Egyptians saw the sun die each dusk and be reborn at dawn. In the cosmic perspective, these poetic insights are quite literally reflected in the behavior of stars. A massive star perishes in a supernova, and from its remnants, new stars and planets will one day form. There's a continuity, an immortality of sorts, not for the individual star, but for the patterns and materials of which it was made. For most of human history, the stars were thought of as eternal and unchanging, the realm of the gods, or the perfect and divine, in contrast to the mortal, mutable earth. Learning that stars are born and die has been a profound shift. It has united the heavens and the earth into a single tapestry of nature. The calcium in our bones and the iron in our blood are proof that we and the stars are intimately connected. The life cycle of a star is not fundamentally different from the life cycle of a flower in a field. There's a sprouting, formation, a bloom, main sequence, a withering, giant phase, and a scattering of seeds, nebula and remnants, to ensure the next generation. It's just on a much grander stage and longer timeline, but the pattern is familiar. We see it in our own lives and in the ecosystem around us. What meaning can one take from this cosmic perspective? Some might find it nihilistic. Everything ends, even starlight dies, and in the far end, nothing remains. But one can also find it deeply inspiring. Death in the universe is not a permanent annihilation. It's transformation. The end of one thing is the beginning of another. The universe wastes nothing, rearranging dead stars into new stars, dead galaxies into new galaxies, on larger scales through collisions, perhaps dead universes into new universes if some theories hold weight. If even the stars, those eternal lights in the sky, must die, then how remarkable it is that out of their death comes something as poignant and wonderful as us, beings made of their dust, able to contemplate the very process that gave us form.
There is also a lesson in humility and gratitude. We gaze at the stars often with a sense of permanence. They seem the fixed backdrop of our lives, but they are on their own journeys from birth to death. We happen to live in a cosmic age rich with stars. It will not always be so. This recognition makes a clear night sky even more cherishable. We are witnessing a phase of the cosmos that, however long, is transient. We are fortunate to see a universe awash in light. The darkness that will come is beyond our personal timescales, but its inevitability makes the present cosmos no less splendid, if anything, more. Above all, the death of stars teaches us that endings can be creative. The stars do not simply vanish, they leave behind gifts. They forge the gold in our rings, the oxygen in our lungs, the silicon in the rocks beneath our feet. They leave behind neutron stars that keep time better than atomic clocks, and black holes that test the limits of physics. Even in their violent final acts, there is a profound generosity. They give themselves to the universe. We too are of star stuff and will return our atoms to the greater pool. In a poetic sense, one could think, as we live, we are a way for the universe to know itself, since our brains are made of those very atoms forged in stars and now contemplating the cosmos. In dying, we give those atoms back so that new forms, new consciousness can one day arise. It's a scientific truth that every atom in our body will outlast us, moving on to become parts of other organisms, the air, the ocean, and over geological time, part of new minerals, or maybe subducted into Earth's mantle, or blown out to space if Earth loses some atmosphere. On very long timescales, perhaps our atoms will cycle through new planets, or even be lofted off Earth when the sun dies. It's a kind of immortality, material, not personal, but comforting in its continuity. As we near the conclusion of our journey, step back and look at the night sky again, perhaps in your imagination if it's not visible right now. See the stars twinkling. Look up at the night sky and breathe in. Feel the air enter your lungs. That air contains oxygen that was created in a red giant star billions of years ago. It contains nitrogen that may have been produced in some long ago stellar factory, carbon from another. The iron in your blood was born in a supernova explosion, traveling through space, eventually finding its way into the cloud that made the sun and planets, and then into your body. Every breath is a connection to that stellar heritage. As you exhale, perhaps some of those atoms will return to the atmosphere, and a plant will take them in tomorrow, incorporating the carbon into a leaf. Years from now, that carbon might be part of a fruit, eaten by another person, and become part of their body. And so the cycle goes on Earth, small echoes of the greater cycle of stars. We are all connected through these cycles. When we gaze at a distant star, we are seeing it often across a great span of time, The light reaching our eyes might have left that star hundreds or thousands of years ago, before the rise and fall of nations, before any living human. In that sense, to look at the stars is to look into the past. We are literally witnessing ancient history. Some of those pinpoints of light are from stars that have already died, their light only now arriving. The cosmos is a memory machine, preserving in the speed of light the images of the past. The night sky could be seen as a grand memorial of stars, some alive, some long gone, but all appearing together to us as if coexistent. We remember the stars by their light, and in turn, we carry the stars' memory within us because we are made of their remnants. The universe has enabled us, beings of matter, to evolve and eventually understand this very fact. Through our studies and stories, the cosmos is remembering itself. Our knowledge of stellar evolution is the universe's self-reflection. We, tiny, ephemeral humans, have figured out how stars live and die. We've collected the whispers of ancient light and decoded the messages of neutrinos and gravitational waves to fill in pages of the cosmic story. In so doing, we are giving voice to the stars that cannot speak for themselves. We are eulogizing them even as we celebrate their role in giving us life.
When you next find yourself under a clear, starry sky, take a moment to feel the depth of time and the cycles at play. That band of the Milky Way is the combined glow of billions of stars at various stages, some just being born in nebulae, some shining in middle age like the sun, some swelling into red giants, some already collapsed into remnants hidden in the mix. Perhaps one of those stars will explode tomorrow and be seen by us in a few thousand years, given distance. Perhaps around one of those stars, new civilizations will one day come to be, using the elements those stars provide.
We are not separate from this grand cosmic web. We emerged from it. We return to it. There is a profound kinship in knowing that the carbon in your cells was forged in stellar hearts. It binds us to the universe, to the stars that died, so that we might live. This knowledge can influence how we see our own lives and deaths, not as isolated events, but as continuing contributions to an ongoing story. Just as a star's death enriches the galaxy, maybe the mark we leave, through our actions, creations, and children, or at least the literal atoms of our body, enriches the tapestry of humanity and life. And so, the death of stars is at once an end and a beginning, destruction and creation fused in one cosmic act. It is a beautiful paradox that the universe appears to operate. Nothing lasts forever, yet nothing is ever truly lost. The atoms always cycle through new forms. The energy finds new channels. Even black holes, which hoard matter and energy, eventually give it back when they evaporate. This journey has been long and filled with wonders, from the quiet death of a sun-like star casting a glowing nebula, to the explosive demise of a supergiant birthing neutron stars and black holes, to the mergers that ripple space-time, to the ultimate fate of a cosmos drifting into darkness. Throughout, we find echoes of our own existence, and perhaps guidance for our own lives. We learn that great energy and growth, like a star's main sequence, eventually yield to change and aging, the giant phase, and finally to transition, death. But we also learn that what comes after can be meaningful. A star becomes a white dwarf that may one day spark a nova and bring new light. Our lives might influence generations ahead in ways we cannot imagine. Under the eternal night, we contemplate these things. The stars do not last forever, but their story does, written in us and around us. In the endless night, we remember the stars, and through us, the stars remember themselves. The quiet death of a sun-like star. It begins with a single light in the darkness. A star, solitary and brilliant, burns in the void. For ages untold, it has been a beacon, a steady,
shining pinprick against the infinite night. Its light has traveled across the cosmos, a silent tale of its life. But now, something changes. The star's shine falters, ever so slightly. Its once unwavering glow begins to dim and flicker like a candle reaching the end of its wick. In this moment, we witness the opening lines of a final act, the beginning of a star's dying. Even the stars are mortal.
For ancient peoples gazing up, the very idea of a star dying would have seemed impossible. The stars were regarded as eternal campfires of the gods, or the fixed points of the firmament. If ever a new star appeared, or an old one disappeared, as happened with rare supernovae recorded in history, they were seen as divine omens, not natural events. Only in modern times have we come to understand that these dramatic changes are the logical, even inevitable progression of a star's life. A star's birth, life, and death are part of the cosmos's story, not the caprice of deities. The star swells imperceptibly at first, then noticeably. Once contained and stable, it now grows bloated and luminous, turning a deeper shade of amber, then red. Its outer layers, no longer tightly bound, drift outward into space. If there were eyes watching from a nearby world, the star's transformation would paint the sky in hues of scarlet twilight, even at midnight. This ancient sun is becoming a red giant, a star near death, casting off the vestiges of its youth. Imagine standing on that distant world. The star that once gently rose and set now looms huge and ominous, filling a quarter of the sky. The air heats, and the ground cracks under a perpetual red dusk. Oceans, if they exist, begin to boil away as the star's dying light intensifies. The planet's sky is on fire. Day and night, a sullen ruby glow suffuses the heavens. For even when the star is below the horizon, its scattered light paints the atmosphere blood red. Any moons or nearby planets that once circled safely now face an inferno. The star's swollen photosphere might even reach out and consume its innermost planets entirely, erasing them in a final act of cosmic devouring. The once life-giving star has become a cosmic furnace, heralding doom. It is a breathtaking and terrifying spectacle, beautiful in its grandeur and heartbreaking in its finality.
Why must even stars die? To answer this, we look into the heart of the star. For eons, in the core of that star, a mighty engine has burned. The star's purpose throughout its long life was to fuse the lightest elements into heavier ones, to take the simplest gas of the universe and forge it into something new. In its core, hydrogen atoms were pressed and squeezed so tightly that they merged into helium, releasing a tremendous burst of energy that made the star shine. This fusion is the star's heartbeat, a constant thrum pushing outward against gravity's incessant pull inward. Every second, countless atoms join together, and with each union, a packet of energy is born and fights its way from the core to the surface, eventually escaping into space as starlight. It is as if the star stands in a delicate balance, a perpetual tug of war, gravity drawing it inward, energy from fusion pushing outward. For a time that seems infinite to us, this cosmic heart pumps steadily, and the star remains in glorious equilibrium, neither collapsing under its own weight nor dissipating into the void. As long as the fusion fire burns in its core, the star lives on, an incandescent beacon of stability. But nothing in the universe is truly eternal. The star's fuel is finite, and one quiet day in the deep future, the fusion fire begins to falter. The hydrogen that sustained it for so long becomes scarce in the core. Like a lamp running out of oil, the light begins to change. With less outward push from the diminishing core fire, gravity tightens its grip. The core, no longer able to support the weight of the star's layers, starts to shrink. And as it contracts, something remarkable happens. It grows hotter, far hotter than it ever was during its placid youth. In that rising heat, a new kind of fire is kindled. The helium ashes,
left from millions of years of hydrogen burning, suddenly become fuel themselves. In a furious flash, 3 helium nuclei slam together to fuse into carbon. The star's heart, which was faltering, gets a new surge of energy. It's like a second wind in old age, sudden, fierce, but short-lived. The core's collapse is halted by this burst of helium fusion. Bolstered from within, the star swells dramatically and becomes a red giant. Now our once small star is a swollen titan. Its outer layers have expanded hundreds of times over, cooling and glowing a rich, coppery red. To any distant observer, this aging star has become an enormous beacon, far larger and more luminous than it was in its youth. Yet its brilliance is deceiving. It is the brilliance of old age, not of vitality. Inside, the star is dying. The helium fuel at its core will not last long. Compared to the billions of years of its hydrogen-burning prime, the helium burns in a relative instant, in only a few % of that time. The star is living on borrowed time, using up its last reserves in a final prodigious blaze. In the star's final breaths, it becomes unstable. It pulsates, expanding and contracting, as if it were a gigantic cosmic lung drawing ragged breaths. Each expansion and contraction is vast and slow, taking perhaps years or decades, but in the life of a star, it is a frantic oscillation. With each pulse, the star sheds some of its outer gas into space, like a series of sighs, creating shells of material that drift away into the surrounding darkness. Between pulses, the star's hot core shines through more clearly, its intense radiation pushing on the remaining layers. A stellar wind, a stream of particles from the star's surface, begins to blow the star's atmosphere outward. The dying star is both lamenting and creating with these breaths, for the gas it expels is rich with elements forged over its lifetime. Carbon formed in the star's core now flows outward in gentle currents. The star is painting its own epitaph in the skies around it, layer by layer. At last, the star can no longer hold onto its outer layers at all. One final large pulse or wind sweeps them completely into space. The great bloated red giant effectively sloughs off its entire outer envelope. All that remains behind is the hot, naked core of the star, now exposed to the cosmic vacuum. For a brief moment in cosmic time, that core, small as it may be, perhaps only the size of Earth or smaller, shines fiercely. It is incredibly hot, having been the furnace at the star's center, and now with no overlying layers to obscure it, it radiates intense ultraviolet light into the space around it. The formerly expelled outer layers, drifting nearby, suddenly find themselves bathed in this energetic glow. They begin to fluoresce, lit up from within like a neon sign. A shell of multicolored gas materializes around the star's core, expanding outward. This is a planetary nebula, the quiet, haunting aftermath of a star's gentle death. Under the gaze of telescopes, it appears as a delicate bubble or ring of glowing gas, expanding gradually into interstellar space. To an eye peering from afar, it might resemble a ghostly flower blooming in the dark garden of the galaxy, a final blossom from the star that was. The colors of this nebula can be vivid, subtle greens and blues from oxygen atoms, reds from hydrogen, all mixing into an ethereal pastel tapestry. The shapes are surprisingly intricate. Some nebulae form perfect spheres or rings, while others are sculpted into hourglass forms or butterfly-like wings by the star's magnetic fields, or perhaps by the gravity of unseen companion stars. At the center of this luminous cloud floats the small stellar core, now called a white dwarf. It is a stellar corpse, extremely hot but fading, shining only with leftover thermal energy. A white dwarf is usually no larger than a planet, yet contains nearly the mass of the original star. It's incredibly dense. The star's mass is now crushed into a sphere perhaps the size of Earth. The matter inside is in a strange, degenerate state.
atoms pressed so close that electrons are squeezed free of their orbits. No fusion fires burn in this core anymore. It glows like an ember taken from a fire, brilliant at first, but destined to dim over the eons as it cools. Such is the quiet death of an ordinary star. A star like this one, perhaps like our own sun someday, does not end in violence, but in a peaceful casting off, a cosmic setting of the stage. Its final act is to illuminate the gases of its own shed self, creating a hauntingly beautiful nebula that will linger for only a few millennia before dispersing into the surroundings. That glowing shell is a brief memorial, a glowing epitaph written in space, commemorating the star's existence. In time, even that nebula will fade, its atoms drifting away to mix with the interstellar medium. In dying, the star returns its substance to the galaxy. The elements it formed, carbon and nitrogen from its later fusion, and even new molecules forged in the cooling breath of its final winds, are cast back into the cosmic reservoir. The star's death is an ending, but also a bequeathing. Its carbon will become the seed of new organic molecules. Its dust may gather into future planets. In this gentle goodbye, the star enriches the universe with the products of a lifetime. Yet not every white dwarf rests quietly forever. If a small star's corpse orbits in a close binary system with another star, it may later find a way to die a second, more violent death. As a white dwarf steals gas from its companion, it grows heavier until reaching a critical weight. At that point, its carbon heart can ignite in one furious wave of fusion, consuming the star from within. In a matter of seconds, the white dwarf is blown to bits, a titanic thermonuclear explosion. This is a type of supernova as well, often called type Ia by astronomers, and it can rival the brightness of a core collapse supernova. In this scenario, the entire star is destroyed, with no neutron star left behind, just an expanding cloud of debris rich in newly forged elements like iron and nickel. Even a star that lived quietly can thus end in sudden violence if given this final push. Such explosions are another way the galaxy is seeded with the heavy elements that will become part of new cosmic generations. The explosive death of massive stars. Now, consider a star far more massive, a true stellar giant many times heavier than our Sun. Such a star, born with tens of times the Sun's mass, lives a very different life and meets a far more dramatic end. Where a smaller star like the Sun quietly sloughs off its outer layers, a massive star lives and dies in raging fire. It is a brilliant blue-white beacon during its life, far hotter and more luminous than an average star. It burns its fuel at a prodigious rate, living fast and dying young, as one might say. For millions of years, a mere blink compared to the billions our Sun will enjoy. This massive star fuses the lightest elements in its core at a feverish pace. Its core temperatures and pressures soar much higher than those in smaller stars, and the chain of nuclear fusion proceeds beyond just hydrogen to helium. Once helium is exhausted, the core, under crushing gravity, contracts and heats again, and new fusion reactions ignite in succession. Carbon burns into neon, neon to oxygen, oxygen to silicon, step by step forging heavier and heavier nuclei. Each new fuel is consumed faster than the last, as if the star knows its time is short and rushes through one element after another. Deep in the heart of this giant, a ball of iron begins to form, and with it, the star's fate is sealed. Iron is a strange endpoint for the star's nuclear alchemy. Unlike the lighter elements, fusing iron does not release energy. Instead, it greedily absorbs energy. All the star's prior steps of fusion had been exothermic, releasing the energy that held the star up. But when enough iron accumulates in the core, further fusion becomes futile. The stellar engine that has thrummed for millions of years suddenly sputters and stalls, as it tries to fuse iron. In a star so huge, this failure is catastrophic. Gravity, which has been held at bay for so long by the outward pressure of fusion, now has no effective counterforce in the core. There comes an instant, a final unforgiving moment, when the iron core can no longer support the enormous weight of the star's outer layers. In the blink of an eye, the core collapses. A star that dwarfs our Sun in size implodes in less than a second. The iron atoms in the core, under the extreme pressure, are crushed together. Protons and electrons merge into neutrons in a burst of particle transformations. The core, which might have been the size of Earth, shrinks to a sphere only a few tens of kilometers across and is as dense as an atomic nucleus. The collapse releases an almost unimaginable amount of gravitational energy, heating the core to billions of degrees. A flood of neutrinos, nearly massless, ghostly particles born of nuclear reactions, erupts from the core and flies outward. In fact, so much energy is carried by these neutrinos that for a brief moment, they outshine the star's luminous output by a factor of hundreds. It is as if the star's soul is escaping in the form of these ghost particles, rushing out in all directions. This is the opening of the most violent event in the star's life. The core collapse triggers a supernova explosion. The infalling outer layers of the star, which were rushing inward following the collapsing core, slam into the now rock-hard wall of densely packed neutrons that the core has become. In that violent collision, the infalling matter rebounds. A powerful shockwave forms and begins to propagate outward. The shock, energized by the deluge of neutrinos streaming from the core, plows through the star's layers, tearing them apart. Within hours, the shock reaches the star's surface and blasts the star apart in one titanic explosion. The star that once shone steadily is now gone, and in its place is a swelling fireball of stellar debris. For a brief time, this single dying star outshines its entire galaxy. What was once a distant point of light now becomes a beacon so brilliant that it can be seen across millions of light years. If there were civilizations looking up from planets in that galaxy, they would see a searing new star light up the sky with ferocious intensity, perhaps casting shadows at night and outshining their moon. On Earth, even though such explosions are rare in our galaxy, humans have recorded a few over the centuries. Ancient sky watchers around the world noted guest stars suddenly appearing in the sky, bright enough to be seen in daylight for weeks. They were witnessing supernovae, though they did not know it, the death flashes of giant stars. In modern times, astronomers have captured many such events in other galaxies. In the late 20th century, they witnessed a supernova in a nearby dwarf galaxy, the brightest seen in almost 400 years. For weeks, it glared in the southern sky, a stark reminder that even the heavens can erupt without warning. A supernova pours out not just visible light, but every form of electromagnetic radiation, from searing X-rays and gamma rays to long, lazy radio waves. It also launches matter at incredible speeds, a hurricane of gas and dust racing outward. The energy of a supernova defies easy comprehension. In those few seconds of collapse and rebound, the star releases more energy than it did in its entire millions of years of normal life. People sometimes say it's like a billion suns lighting up at once. If a supernova were to occur within a few dozen light years of Earth, it could outshine our moon and potentially disrupt the biosphere with its high-energy radiation. Yet, from a safer distance, it would be one of the most glorious sights in the universe. A cosmic firestorm, the sudden blossoming and slow fading of a star's last light. And amidst this destruction, there is creation. In the heart of the supernova explosion, the chaos and heat forge new atomic nuclei that the star never could while it lived. The shockwave's extreme conditions allow atoms to slam together and capture neutrons rapidly. Elements heavier than iron,
which the star could not produce in its normal life, are manufactured in these brief moments of fury. Gold, silver, platinum, iodine, uranium. The universe's precious metals and rare elements are born in the crucible of the exploding star. Before stars, the universe held only the lightest elements: hydrogen, helium, and a dash of lithium from the Big Bang. All the rest, carbon and oxygen, iron and gold and beyond, were forged in stellar furnaces and in these titanic explosions. In this way, almost every element heavier than helium is a gift from stellar lives and deaths. Atomic nuclei absorb neutrons in rapid succession. Later, those neutrons decay into protons, transmuting the elements into heavier ones on the periodic table. The star, in dying, becomes an alchemist on a cosmic scale. The brilliant glow of the supernova begins to be tinged with the spectral signatures of these freshly minted elements. When the debris eventually cools enough, these atoms will combine into dust grains, floating through space, awaiting incorporation into future worlds. Thus, the star's violent death is also a moment of genesis, the birth of new materials that will enrich the galaxy. What remains after such a cataclysm? As the glare of the supernova fades over weeks and months, and the expanding cloud of ejected gas thins out, we peer into the aftermath to find a newborn object at the center. If the original star was massive but not too extreme, perhaps up to 20 times the Sun's mass, the core that's left behind is a neutron star. This neutron star is a tiny, ultra-dense sphere, only about as wide as a city is long, yet containing more mass than the entire Sun. It is essentially a giant atomic nucleus, a ball of neutrons packed shoulder to shoulder. In fact, the first supernova explosion observed by ancient skywatchers, a guest star in the 11th century, whose remnants form a beautiful nebula visible today, left behind a neutron star that still sits at the center of the expanding cloud, spinning and flashing. For a neutron star is not a quiet thing, at least not at first. Neutron stars, pulsars, and magnetars. Often, the newborn neutron star is incredibly hot and endowed with a rapid spin inherited from the core of the star that collapsed. Conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull in their arms, means that a core that was spinning moderately will whirl madly as it shrinks. A neutron star can rotate dozens or hundreds of times each second. Along with this spin, it carries an immensely strong magnetic field, intensified by collapse, just as the spin was. The result is one of the universe's most astonishing phenomena: a pulsar. Bright hotspots form at the neutron star's magnetic poles, where intense beams of radiation shoot outward. As the neutron star rotates, these beams sweep around like the lighthouse beams on a dark shore. If Earth lies in the path of those beams, we see the neutron star blinking on and off regularly. A cosmic lighthouse marking the location of the lost star. When the first pulsar was discovered in the 1960s, its signal was so regular, a pulse every 1.3 seconds, that the astronomers half-jokingly named it LGM-1 for Little Green Men, thinking it might be an artificial beacon. Soon they found more and realized these were not alien signals, but the heartbeats of dead stars. These neutron stars are among the strangest objects in existence. A teaspoon of neutron star material on Earth would outweigh a mountain. The gravity at its surface is so immense that if you dropped a marshmallow from a few feet above, it would hit the surface with the energy of a nuclear bomb. The neutron star's magnetic field is trillions of times stronger than Earth's. In some neutron stars, called magnetars, the field is so ferocious that it can distort the very structure of atoms and unleash bursts of high-energy radiation. Magnetars occasionally experience starquakes as their rigid crusts crack under magnetic stress, releasing tremendous flares of gamma rays. In 2004, a magnetar on the other side of our galaxy erupted, and even from tens of thousands of light years away, it briefly ionized Earth's upper atmosphere. These exotic stellar remnants may be small, but they can be more energetic in certain moments than almost anything else in the cosmos. The neutron star gradually cools and slows its spin over many millennia, especially if it has no companion feeding it fresh energy. Its lighthouse beams dim. In the far future, that neutron star may become practically invisible, a cold, dark sphere of neutron matter drifting silently through the galaxy like a spent coal from a great fire. But at least initially, in the aftermath of the supernova, it is very much an active presence, a cinder with a fiery glow. In some supernova remnants, the neutron star's wind of high-energy particles continues to energize the ejected gas long after the explosion, making the nebula glow in fantastical shapes and colors. If the original star was even more massive, say on the order of 20, 30, or more times the mass of our Sun, then even the neutron star outcome is denied. In these cases, the core that tries to form a neutron star might be so heavy, more than a few times the Sun's mass, that not even the degenerate pressure of neutrons can hold it up against gravity. Nothing in nature can withstand the gravitational crush of such a massive core. Black holes, the ultimate collapse. In that case, the core collapses further, past even the neutron star stage, and vanishes from view entirely. The star's core becomes a black hole, an object so dense and with gravity so strong that within a certain boundary, not even light can escape its pull. Around this collapsed point lies the event horizon, the spherical surface marking the point of no return. Space and time themselves are warped around this region. If we could watch the dying massive star's final moment of collapse to a black hole from a safe distance, we would never actually see it disappear. Instead, we'd see the star's image freeze and dim as the last light it emits gets stretched to redder and redder wavelengths, time appearing to almost stop at the brink of the event horizon. In reality, the star's core continues to collapse beyond our view, but the information about it is forever hidden behind that horizon. The newly formed black hole now contains the mass of several suns in a sphere only a few kilometers wide. Its gravity is a pit from which nothing escapes. A black hole is the most extreme remnant of a star. The core of the star has been compressed beyond any known limit. At the center lies a singularity, a point of almost infinite density, shrouded by the event horizon. But contrary to popular myth, a black hole is not a cosmic vacuum cleaner indiscriminately devouring everything in sight. If our Sun could be instantly replaced with a black hole of the same mass, Earth's orbit would remain unchanged, though our world would freeze without sunlight. One has to get very close to a black hole, inside the Schwarzschild radius, to be irretrievably pulled in. Sometimes, the demise of a very massive star can create an even more spectacular signal. If the star was rapidly spinning and had strong magnetic fields, the collapse into a black hole can produce jets of material shooting outward from the poles at nearly the speed of light. These jets drill through the collapsing star and burst out into space as intense beams of gamma rays. We call this event a long gamma ray burst. For a few seconds, a gamma ray burst from a collapsing star can be the brightest electromagnetic event in the observable universe, detectable across billions of light years. It's a dying star's last scream, a focused, deadly burst of energy indicating the birth of a black hole. Satellites have recorded many gamma ray bursts, and in some cases have spotted the faint afterglow from the exploding star's remains, confirming that they were indeed massive stellar explosions, likely linked to black hole formation. In rare cases, a massive star might even collapse directly into a black hole with no supernova explosion to herald it. The star's core simply implodes and keeps imploding as the infalling outer layers follow it past the event horizon. From the outside, one might witness the star suddenly dimming and disappearing, as if a trap door opened beneath it. For a brief moment, there could be a burst of neutrinos or a slight gamma-ray flash, but no brilliant supernova blast. Such an event is sometimes termed a failed supernova. In recent years, astronomers identified a candidate, a massive star in a nearby galaxy that brightened slightly, then faded away to nothing, leaving no trace. It seems that nature can be both extravagant and miserly with its farewells. Some stars go out in a blaze of glory, while others quietly wink out, leaving darkness and a newfound black hole where once a star shone. As many as a third of the most massive stars may die in this undramatic way, simply collapsing into the void. These are truly the most secretive of stellar deaths. Aftermath, ghosts and rebirth. Whether through a titanic supernova or a quiet collapse, the end of a massive star leaves space forever changed. The debris cast off from the explosion races outward at millions of kilometers per hour, a shockwave plowing into the surrounding interstellar gas. Over years and decades, observers with telescopes can see this shell of debris expanding, a ring of sorrow growing larger but fainter as it dissipates its energy into space. This glowing remnant, enriched with all those new heavy elements, mingles with the interstellar medium, the tenuous gas between stars. In time, that gas may become the raw material for new stars and planets. A supernova's remnants are like the scattered ashes from which new life will emerge, glittering, multicolored nebulae cooling into the darkness. Sometimes, amid those remnants, the core that was left behind makes its presence known. In one famous supernova remnant, a pulsar spins madly, lighting up the surrounding cloud with pulses of energy and winds of particles that cause the gas to glow. In other cases, if the remnant core was a black hole, we might see high-energy X-rays or gamma rays if the black hole is consuming material around it. Often, however, the black hole simply is, unseen, its gravitational field the only testament to a star that once shone. Now our journey takes an even stranger turn. The death of one star, spectacular as it is, can give rise to an even more dramatic event under the right circumstances. Consider a binary star system, two stars orbiting one another in a celestial dance. If both stars are massive enough, both might eventually become supernovae in their time, leaving behind two neutron stars orbiting their common center. Over millions of years, their gravitational dance continues, but with each orbit, they draw imperceptibly closer. Their spiraling movement generates gravitational waves, ripples in the very fabric of space-time, that carry energy away and bring the neutron stars ever nearer to collision. Kilonovae, cosmic collisions and gravitational waves. Finally, long after they were born, these two city-sized remnants meet their fate together. They collide and merge in a violent embrace. In that moment, a new kind of fire ignites. The merging of two neutron stars creates an event we call a kilonova, a cosmic flash that, while not as bright as a supernova, shines 1,000 times brighter than an ordinary nova. For a few days, the site of the merger glows with a blue then red light. It is an event both fierce and brief, a final fireworks display from the corpses of stars. The physics of this collision is extraordinary. When neutron stars merge, their incredibly dense matter gouges and shocks itself, forming exotic heavy elements in profusion. If supernovae are one forge for the heaviest elements, kilonovae are another, perhaps even more prolific for certain treasures. In the debris tossed out by the merging neutron stars, astronomers have detected signatures of gold and platinum being created in astonishing quantities. In mere seconds, more gold may be forged than in all the cores of stars over billions of years. The kilonova's glow is powered by the decay of these new, unstable heavy atoms as they release energy. Alongside the light of the kilonova, the merger rings the universe like a bell. Gravitational waves ripple outward from the collision, stretching and squeezing space-time itself. By the time these waves reach us, they are faint echoes, but with sensitive instruments, we have learned to listen for them. In recent history, humanity has detected such ripples, hearing the chirp of two neutron stars colliding in the depths of space. In tandem, telescopes caught the delicate afterglow of the kilonova, marking the first time we both saw and heard a cosmic event of this magnitude.
In some neutron star collisions, the two merging stars might collapse into a black hole immediately after the merger, swallowing some of the heavy element-laden debris. In others, they might form an extremely massive neutron star that survives for a brief time. But either way, they leave a changed environment rich in freshly minted elements. These elements will drift through space, become part of gas clouds, and one day be incorporated into new worlds. It is awe-inspiring to realize that the gold in a ring on a person's finger likely came from such a merger of two long-dead stars, billions of years ago in our galaxy. The violence of that moment becomes the gentle gleam of metal we see and cherish, a direct connection between cosmic catastrophe and human ornament.
Observing stellar death. Throughout all these scenarios, humanity has slowly learned to read the messages in the skies that reveal these processes. How do we know these tales of dying stars when no human has watched a single star go through its entire life cycle? The truth is, the universe has left clues for us, and with our ingenuity, we have learned to gather them across the light years. We piece together the story of stellar death from many different kinds of observations across many types of cosmic messengers.
First and foremost, we see the light. Visible light from supernovae has been recorded by sky watchers for millennia. From the sudden appearance of guest stars noted in ancient chronicles to the careful telescopic monitoring of distant galaxies by modern astronomers who catch supernova flickering into brightness like cosmic fireflies. We have captured images of glowing planetary nebulae around dying sun-like stars, each a snapshot of a star's final sigh. We have seen the expanding shockwaves of supernova remnants, their tendrils growing over years in photographic time-lapse, confirming that they are indeed blasts in slow motion. But light is just one messenger. We have also learned to detect radio waves, which reveal phenomena invisible to our eyes. In the radio spectrum, pulsars announce themselves clearly. Their lighthouse beams become pulses of radio emission that our radio telescopes can pick up. The very discovery of neutron stars came from radio astronomy. To this day, radio observatories map the intricate structure of supernova remnants, picking up the radio glow of electrons spiraling in magnetic fields there. Through radio eyes, we have seen the remnants of star death stretching across vast swaths of sky, invisible in ordinary light. Then there are the neutrinos, those ghostly particles that rarely interact with matter. When a massive star's core collapses, an enormous number of neutrinos are released. In one famous supernova, underground detectors on Earth registered a sudden burst of neutrinos, a full few hours before the supernova's light became visible in the night sky. Those neutrinos had raced out from the collapsing core, heralding the death of the star before the light from the explosion could fight its way out. It was the first and only time so far that we directly detected such a neutrino burst, and it confirmed our theories about what happens inside a dying star's core. Now we wait eagerly for the next nearby supernova, knowing that neutrino detectors will ring like alarm bells, perhaps even allowing us to witness the core collapse in neutrino signals ahead of the light show. In recent years, we have opened our ears to the gravitational waves, adding a whole new sense to our astronomical repertoire. When massive objects like neutron stars or black holes collide, they send out ripples in space-time that travel across the universe. Detectors on Earth have picked up these tiny distortions as they pass by. Through gravitational waves, we heard the final moments of binary black holes merging, events completely dark to electromagnetic telescopes. We also heard, and then saw, a pair of neutron stars collide and light up a kilonova. Gravitational waves have allowed us to confirm directly that yes, black holes and neutron stars do merge exactly as long predicted, releasing energy not as a flash of light, but as a faint trembling of the cosmic fabric. It's as if we developed the sense of hearing after millennia of only seeing. Whole new phenomena have become perceptible. Each type of messenger, light, radio waves, neutrinos, gravitational waves, gives us a different insight into the death of stars. By combining them, an incredibly detailed and holistic picture emerges. For example, by studying a supernova's light alone, we learn about its energy and composition. By catching neutrinos from it, we peer directly into the core collapse physics. By listening for gravitational waves, we might witness the formation of the neutron star or black hole in real time. The universe has been gradually revealing its story through these multiple channels, and we have become adept at tuning in. Armed with this knowledge, we can turn our attention to the star that matters most to us, our Sun. The Sun is a fairly ordinary star, midway through its life, but one day it will undergo its own deathly transformation. It will not explode as a supernova. It lacks the mass for that ferocious end, but the Sun's demise will nonetheless be a dramatic and profound event, especially from the perspective of any living beings that might witness it. The fate of our Sun. In about 5 billion years, an unimaginable span to us, yet a fixed and finite countdown in cosmic terms, the Sun will exhaust the hydrogen fuel in its core. As it begins to run out of gas, the Sun's core will contract and heat up, and, just as we described for a smaller star's final stages, helium fusion will ignite. Our star will swell into a red giant. In those distant days, the Sun will expand to hundreds of times its current diameter. Mercury and Venus, the inner planets, will almost certainly be engulfed, devoured by the Sun's bloated fiery plasma. Earth's fate is less certain. Some calculations suggest it might just escape engulfment, spiraling outward a bit due to the Sun's mass loss. But even if it isn't swallowed whole, it will be scorched and sterilized. The oceans will boil off, the atmosphere will escape, the surface will become a molten hellscape. For any distant observer in those future times, our Sun's transformation will be a sight to behold. What was once a gentle yellow star will balloon into a red monster dominating our solar system. In the solar system's far future, perhaps an intelligent species, whether human descendants or some other beings, might watch the Sun's angry metamorphosis from a safe haven, maybe on the moons of Jupiter or Saturn. They would see the Sun, day by day, grow larger and redder, its brilliance tinged blood orange. The familiar constellations might fade in its overwhelming glare. The heat would rise even in the outer solar system. By then, Earth, if it still exists, would be a glowing ball of magma. Eventually, as the Sun reaches the apex of its giant phase, it will begin to pulsate and cast off its layers. It might produce a beautiful planetary nebula of its own. Our Sun, which once lit the solar system with a crisp golden light, will create a vast bubble of fluorescent gas, expanding outward past the orbits of the inner planets. At the center of that nebula will shine a pinpoint of intense white light, the Sun's core laid bare as a new white dwarf. Imagine, for a moment, what that will look like from a vantage point at the edge of the solar system. Perhaps from the twilight skies of Pluto, or some dwarf planet far beyond Neptune, one might see the whole sky dominated by the glowing cloud of the Sun's planetary nebula. It could appear as a huge, circular rainbow cloud, slowly fading over thousands of years. The white dwarf Sun would be incredibly luminous in ultraviolet, causing the nebula to fluoresce. In time, the nebula would disperse, and all that would remain of our Sun would be that white dwarf, a hot,
Earth-sized ember composed mostly of carbon and oxygen, the products of helium fusion in the sun's final throes. It will shine bluish-white at first, equal in brightness to perhaps 1,000 present-day suns. But being so small, it will cool and fade over billions of years. Eventually, long after the planetary nebula dissolves and blends into the galactic background, the sun's remnant will become a black dwarf, effectively invisible. Our solar system will not be spared the universal law of change. The surviving planets, perhaps Mars, Jupiter, Saturn, and the outer worlds, will find themselves orbiting a tiny, dense star where once a bright sun shone. The night sky on those worlds will be dark, the familiar warmth and light of the sun replaced by a dim pinprick. Perhaps, in that far future, nothing of Earth remains but some drifting debris or baked rocks orbiting the white dwarf. Or maybe Earth's material will have been blown into the planetary nebula, its atoms mixing with the sun's, and eventually traveling outward. In that case, part of what was once our world will eventually become incorporated into new star-forming clouds elsewhere. It's a melancholy vision, the extinction of sunlight as we know it, the end of Earth as a living planet. Yet, viewed from a broader lens, it is also beautiful. The sun's death will contribute to the ongoing cycle of cosmic renewal. The elements from our sun and Earth will be redistributed. Perhaps, many billions of years hence, some of those atoms might find themselves in new star systems, potentially part of new life forms that will walk on new worlds and look up at their skies, never knowing that the atoms in their bodies once warmed a place called Earth, under a star that died to make their own existence possible. The cycle of stellar life and death thus directly touches the cycle of life and death on planets.
The end of starlight. Looking even further into the future, beyond the fate of individual stars like our sun, we confront the ultimate destiny of starlight itself. The universe is almost 14 billion years old now, and it is ablaze with stars. But it will not always be so. Trillions of years from now, the era of starlight will wane. The great spiral and elliptical galaxies we see today will have merged and transformed. Star formation, which requires dense clouds of gas, will slow and eventually cease as those clouds are used up or dispersed. The remaining stars will age and die without replenishment. The cosmos, now so full of glittering galaxies, will grow darker and quieter. The last stars to shine will be the low-mass red dwarfs. These tiny fires burn their fuel so slowly that none have died yet in the current age of the universe. A red dwarf with just a fraction of the sun's mass can fuse hydrogen not only in its core, but throughout its churning interior, eking out its fuel with extreme thrift. Some red dwarfs are expected to live for trillions of years. But even their time will come. Eventually, even the smallest stars will exhaust their hydrogen. Unlike the sun, a red dwarf may not become a red giant in a dramatic flourish. It lacks the mass to ignite a shell of helium in a grand expansion. Instead, when a red dwarf finally runs out of fuel, it will quietly contract and heat up, turning into a hotter blue dwarf stage, according to theory, then gradually cool and fade. It may bypass the classic planetary nebula stage entirely, ending up as a helium-white dwarf, if it was very low mass, or a mostly inert ball of helium and other elements. In either case, its light will slowly dim to blackness. Because the universe is not yet old enough, we have never seen this final stage of a red dwarf, but we know it must happen. In that far future, galaxies will be populated mostly by stellar remnants, white dwarfs, neutron stars, black holes, and perhaps a few slowly cooling red and brown dwarfs. The fading of all stars will usher in the so-called degenerate era of the universe. Picture the cosmos at that time. Galaxies have gravitationally merged into enormous clusters or been flung apart by the accelerating expansion of the universe. The night sky of a planet, if planets still exist, orbiting a black dwarf might be nearly completely dark. No new stars twinkle, only the occasional flicker of a distant supernova from a galaxy still having a last gasp of star formation, or perhaps the weak glow of a sparse constellation of fading red dwarfs. Over exceedingly long times, even those faint lights will wink out. The universe will become a quieter place. Gravity will continue to sculpt the fates of these remnants. In galaxy cores, more black holes will merge and grow. Some stray white dwarfs or neutron stars might collide, producing one last supernova or kilonova here and there, a final cosmic fireworks to break the deepening night. For instance, two orbiting black dwarfs, the end states of most sun-like stars, might eventually inspiral and merge due to gravitational wave emission, creating a brief flare of energy or even igniting a strange supernova if they somehow fuse into a new massive object. Or, as speculative physics suggests, in an unimaginably distant future, quantum tunneling could cause heavy elements in an extremely cold white dwarf to undergo fusion, triggering a so-called black dwarf supernova. If this happens, these would be the last dazzling blasts of the universe, silent, forlorn sparks as the cosmos sinks into dormancy. As time stretches on, if our understanding of particle physics is correct, protons, the hearts of atoms, might be unstable over stupendously long timescales. If proton decay is real, then given enough time, even the matter comprising the dead stars will dissolve. The solid iron in a black dwarf, the neutrons in a neutron star, all could eventually decay into lighter particles, turning the remnant entirely into radiation and perhaps leptons, like electrons and positrons. If protons don't decay, then these remnants might persist essentially forever, but even then, they won't shine or significantly interact. They'd be eternal dark monuments. Black holes, the last truly gravitationally bound structures, also have their own endgame. Through Hawking radiation, a quantum mechanical process where black holes can slowly leak particles and energy, even black holes will eventually evaporate. A black hole the mass of the Sun would take an outrageous amount of time to evaporate, far longer than the current age of the universe. More massive ones would take even longer, practically enduring for eternity on human timescales. But given enough time, even these giants will eventually fizz away, each ending in a final weak burst of light as their last energy radiates into the void. After all of this, the universe will have reached a state often called heat death, or the Big Freeze. No organized sources of energy remain, just a thin soup of particles and photons gradually tending toward a uniform temperature as everything expands. The era of starlight will be a distant memory. The universe, born in fire and sustained for eons by the light of trillions upon trillions of stars, will pass into an age of darkness. It is a sobering picture, a cosmos without stars, without warmth, without structure beyond the quiet drift of elementary particles. One might wonder, what was the point of all these brilliant lives of stars if it all ends in such stillness? It forces us into existential contemplation. But within that grand arc, from bright beginning to quiet end, lies a profound truth. During the epochs when stars shone, so much happened. Stars lit up the galaxies, made possible the existence of planets and life, and gave the universe complexity and beauty. Their deaths, especially, were crucial. Without the dying of stars, the universe would be sterile. The heavy elements needed for rocky planets, for water, for the chemistry of life. None of those would exist without supernovae and kilonovae. Dying stars seeded the universe with diversity. We are made of stars. We ourselves are living proof of the productive value of stellar death. Every one of us is made of stardust. This phrase has been said so often that it risks sounding cliché, but it is profoundly, literally true. The carbon in our muscles and skin was created by a star of moderate mass in its red giant phase, gently blown into space before that star became a white dwarf.
The iron in our blood was forged in the core of a massive star and dispersed in a supernova explosion. The calcium in our bones, the oxygen we breathe, the phosphorus in our DNA, all were synthesized in stellar furnaces and spread through stellar farewells. Even elements like gold that adorn our rings or electronics were fashioned in the extreme environment of merging neutron stars. We are, in a very direct sense, the ash of stars, molded into conscious beings who can contemplate the cosmos. The deaths of stars made our lives possible. Their endings were our beginnings.
Think about it. The gold in a wedding ring was flung into space by the merger of neutron stars in some ancient cataclysm before the Earth existed. The nitrogen in the DNA of every living cell was created in an aging star's envelope and gently blown into space by a stellar breeze as it died. The iron that binds oxygen in your blood was minted in the core of a massive star and scattered across the galaxy by a supernova's shockwave. Each of us carries the story of star death in our bodies. When we gaze at the night sky, we are looking at the past, not just the light from distant stars, but echoes of events that made our own existence possible. In this way, the death of stars is not merely an end, but a transformation. In their destruction, stars sow the seeds of creation. From the wreckage of a supernova, new solar systems will one day form. In the glowing planetary nebula of a gentle star's passing, the gas will mix and mingle into the galactic clouds that spawn new generations of stars. Stellar death rejuvenates the cosmos, keeping it enriched and diverse in composition. There is an existential poetry in this cycle. The stars do not live forever, and neither will the universe as we know it. But in their fleeting lives, they build the complexity that allows future wonders to emerge. They sacrifice themselves to give light and elements to the next generation. Without the death of countless stars before our sun was born, our planet could not have rocks or water or life. We owe our existence to 1 billion stellar funerals. As we close this journey, imagine once more that single star fading from the sky. Its light, which may have shone on ancient oceans of some far-off world, now dims. To any living creatures depending on it, this would be a catastrophe beyond comprehension, a slow apocalypse. And yet, in the cold and dark aftermath, the materials shed by that star will drift and eventually coalesce into new forms. Perhaps a new star, smaller and steadier, will one day form from that very material, and around it new planets. What was once a day's end for one world might become the dawn for another. The universe is a grand tapestry of beginnings and endings, and the death of stars is one of its most stirring threads. It reminds us of the impermanence of even the mightiest engines of creation and the interconnectedness of all things. Through stellar death, the cosmos teaches a simple lesson. From endings come new beginnings. Each flicker and flash, each quiet extinguishing, leaves something behind for those who follow. In our minds, let us wander under a sky full of stars, knowing that above us are not just points of light, but stories. Each star is a story of a life that will someday end, of an element factory that will one day shut down, of a light that will dim. And among those stars, one is our own sun, quietly burning, biding its time. Far in the future, on a planet that by then may only be a memory of what once was, the sun will paint the sky red in its final act, and scatter the elements of Earth and life back into space. Yet even as that seems like a melancholic fate, realize this: those same elements will not disappear. They will become part of something new. The atoms will rejoin the cosmic dance, perhaps to be incorporated into a new star, a new planet, a new life form in the distant future. In this, there is a kind of immortality, not of individual forms, but of the building blocks, the information, the stardust that cycles endlessly. We too are participants in this cosmic cycle. One day, Every element of our bodies will return to the cosmos, perhaps drifting in space, perhaps locked in rock, perhaps pulled into the fires of a future star. And so, standing here, we are an ephemeral arrangement of eternal things. The stars died to give us life, and in time, we will give our elements back to stars. The light of a single star that died millions of years ago might be falling on your face as you look at the night sky. You are witnessing a star's elegy long after its death. But also, consider that the breath you just took contains argon atoms exhaled by countless beings before you, and carbon once formed in the core of a star, billions of years gone. The cosmos flows through us. In the end, as we reflect on dying stars, we find that their story is our story. A story of creation and annihilation, of despair and hope, of an endless cycle in a universe that itself may one day fade. It is a story that evokes humility and wonder. Humility in the face of the vast timescales and forces at play, and wonder at the fact that we can be here, pondering it all, products of the very phenomena we seek to understand. Every dying star whispers to the universe, "I was here, I shone, I mattered, and I matter still, for I give of myself so that others may shine." In the grand darkness that will eventually engulf everything, the echoes of their light and the material they spread will be the legacy they leave behind, just as we hope in our brief lives to leave some legacy, some influence on the future. So the next time we look up at the stars, let us not only admire their present glory, but also honor their fate. They will perish, as all things do, but from their sacrifice comes the possibility of new light, new worlds, new wonders. In the death of stars, there is both the tragedy of an ending and the seed of creation. We journeyed from the gentle dimming of a single star to the cataclysmic collision of stellar remnants across eons and into futures far beyond human imaginings. And through it all runs a common thread. In each finale, there is a quiet grace or a violent flourish that ensures the cosmos is never left unchanged. The dying star is not just an endpoint, it is a catalyst. As we conclude this cosmic tale, let's hold on to the image of starlight slowly fading, and then remember that even as it fades, somewhere else, perhaps due to that very fading, a new light will eventually spark. We are connected to those moments. We are the universe witnessing itself, understanding itself in bits and pieces. Our narrative ends where it began, with the light of a single star. Once upon a time, a star lived and died so that, much later, we could exist and ask why. One day, our sun will die, and from its death, new possibilities will arise that we cannot foresee. This knowledge is not cause for fear, but a gentle reminder of our place in a vast, ever-changing universe. Under the same cosmic sky, generations to come may tell the story of the star that gave them life, just as we tell the story of those that gave us life. In this way, the universe's endless cycle of starlight and darkness, of dying stars and rebirth continues, a story written across the cosmos in light and ash. And as long as there are eyes to see and minds to wonder, the legacy of dying stars will never truly fade, for we remember them in our very being. Every breath we take, every element that courses through our veins, is starlight remembered, a testament to the stars that lived and died to make our life possible. We inhale starlight, we exhale gratitude. The cosmos lives on through us, as we live because of it. And when the night is darkest, and one by one the stars above flicker out, we will still carry the memory of their light within us. For in a way, we are that light, given form and thought. This is what dying stars have given us, the chance to behold the universe's grand design, to feel wonder, and to understand. Though the stars must die, their story, and our story, is unending. In our atoms, in our hearts,
In the endless chain of cosmic creation, the light of the stars lives on. We are, all of us, starlight remembered, shining long after the source has gone out. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark. Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition, and a host of dwarf planets and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness,
having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin, cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, the upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding.
For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, And in civilizations as far-flung as Babylon, India, and China, elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an 8th planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich Darest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer,
hunted for this theoretical planet in the early 1900s, driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death, the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small, icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet, along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the Sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials and initially not so different, they have since diverged into 4 dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the 4 inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns,
splashed across its dark grey terrain, and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long, because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn-out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal. But a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees Celsius everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the Sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic, yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold on to a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe, but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation,
especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the Sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the Sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth-like. All the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth. Its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In some, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds, a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the fifth planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, as pressure increases, hydrogen gas gradually becomes a supercritical fluid, and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared.
far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The four largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system. Its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark, cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics.
a disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down, likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole, a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen-helium mixture in the upper layers and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Titan, is one of the most intriguing objects in the solar system. Titan is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Titan is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few % methane. For a long time, that smog hid Titan's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Titan has rivers, lakes and rain, but of liquid methane and ethane instead of water. At Titan's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Titan's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Titan, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Titan's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space, feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules. And it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger-stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers distance below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the seventh and eighth planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth-based telescopes and Hubble started seeing signs of weather: bright white cloud caps, dark spots, and streaky clouds. Uranus, it turns out, has a dynamic atmosphere that awakens when the Sun's heating is distributed more evenly. During the 2010s, astronomers observed some storms with ferocity comparable to Neptune's, including one huge storm in 2014 that was surprising given how far from the Sun Uranus is. Most of the time, though, Uranus is tranquil looking, with gentle banding visible in enhanced images, and a serene aquamarine hue due to methane in its atmosphere, absorbing red light and reflecting blue, green. At cloud tops, Uranus is a frigid 215 degrees Celsius. Uranus also comes with rings and moons. It has a set of thin, dark rings made of radiation, darkened ice, and dust. They are narrow, kept in line by shepherd moons, and not nearly as showy as Saturn's, but they form a delicate series of hoops around the sideways planet. Uranus's moons include Titania, Oberon, Ariel, Umbriel, and Miranda. They are icy, cratered worlds, a few showing evidence of past internal activity. Miranda, for instance, displays one of the strangest surfaces in the solar system: patchwork regions of ridges and valleys next to older cratered terrain, and a cliff estimated at 20 kilometers high.
a fall from which would take 15 minutes in Miranda's weak gravity. It's as if Miranda was shattered and reassembled or underwent partial melting that froze in bizarre patterns. The larger moons have lesser quirks. Ariel has relatively few craters and signs of youthful resurfacing. Titania has giant canyons. Uranus's moons, like the planet, roll on their sides as they orbit which means, at solstices, one hemisphere of each moon is in continuous sunlight and the other in darkness. What seasonal effects that might cause on those frigid surfaces, we don't really know yet. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun, taking 165 years for one circuit. It's very similar to Uranus in size and composition, but Neptune is notably more active and more intense in color, a deep azure blue. Discovered in 1846 by mathematical prediction, Neptune was visited by Voyager 2 in 1989. Voyager 2 found a dynamic atmosphere, a great dark spot in the southern hemisphere and bright white clouds zipping around. Neptune's winds are the fastest in the solar system, up to 2,100 km/h, especially around those dark oval storms. The great dark spot seen in 1989 was a large high-pressure system exposing darker gases below, roughly the size of Earth, and it vanished a few years later. But other dark spots have since appeared and faded on Neptune. Unlike Jupiter's huge stable spot, Neptune's seem to be shorter, lived storms that come and go every decade or so. Neptune's upper atmosphere is about 200 degrees. Intriguingly, Neptune, like Jupiter and Saturn, radiates about 2.6 times more heat than it gets from the Sun, likely due to residual heat from formation. This internal energy might help drive the vigorous weather we see. Neptune's seasons last over 40 years. We haven't observed a full Neptunian season change yet, but in the decades since 1989 to the 2020s, we've seen some puzzling climate changes. The global temperature in Neptune's stratosphere actually dropped by about 7 degrees Celsius from 2003 to 2018. Then the South Pole suddenly warmed by 11 degrees from 2018 to 2020. It's a reminder that these far-off atmospheres can have variability we don't fully grasp yet. Neptune, too, has rings and moons. It sports faint rings with clumpy arcs. The outer Adam's ring has segments named Liberty, Equality, and Fraternity, where dust is clustered, for reasons initially mysterious until moonlets were found that shepherd those arcs. And Neptune's moon's number 14 at last count. The standout is Triton, Neptune's largest moon, which orbits backward relative to Neptune's rotation. Triton is a captured Kuiper belt object, likely snared by Neptune's gravity long ago. Triton is an ice world almost as big as our moon, with a young surface of frozen nitrogen, water ice, and weird cantaloupe terrain, and it is geologically active. Voyager 2 saw geysers on Triton, dark plumes of nitrogen gas and dust spraying up from the surface, carried by winds before falling. These are essentially cryovolcanoes driven by seasonal heating of Triton's south polar cap. Triton's thin atmosphere is about 1/70,000th Earth's pressure, but enough to have winds that bent those geyser plumes. Triton is extremely cold, yet it still has this slight atmosphere and active geysers, an astounding find. Triton likely has a subsurface ocean as well, kept liquid by residual internal heat or past tidal heating. Because of its retrograde orbit, Triton is slowly spiraling inward toward Neptune. Billions of years from now, it may either break apart into a spectacular ring or crash into Neptune. Neptune's other moons are much smaller and ice, rocky. Nereid has an extremely elongated orbit. Proteus is the second, largest, but still irregularly shaped. It's as large as an object can get without its gravity crushing it into a sphere. Proteus, dark and heavily cratered, might have avoided melting into a sphere by forming late, after the solar system calmed down. Tiny Hydra and Naiad and others zip around Neptune in closer orbits, some in complex resonant dances. Neptune's moon system likely lost whatever original satellites it had during Triton's capture. What we see now are either captured asteroids, comets, or fragments of an ancient moon system reassembled in new orbits. Thus, the outer solar system presents grandeur quite different from the inner. Here we have giant globes of gas and ice, lacking solid surfaces, but adorned with storms larger than Earth and delicate rings. We have an array of moons that are worlds in their own right, some sterile and cratered, others with subsurface oceans or thick atmospheres or erupting geysers. The giant planets act as architects and guardians of the solar system. Their gravity shaped the orbits of countless smaller bodies and may have steered water, rich comets toward the inner planets, possibly delivering Earth's oceans. Jupiter, especially, has shielded the inner solar system at times by vacuuming up comets, though it can also fling asteroids our way if they get too close. The giants likely migrated early on, scattering the debris disk and causing the late heavy bombardment that peppered the inner worlds with craters, and perhaps ejecting leftover planetesimals to form the distant Oort cloud of comets. As we leave Neptune behind, we pass into the realm of icy debris, the Kuiper Belt and beyond, where the sun's influence wanes. Yet even here we find worlds of consequence, the dwarf planets, which challenge how we define planethood and carry clues to the solar system's origin. Dwarf planets, worlds at the edge, and the definition of planethood. Far beyond Neptune's orbit, the solar system continues into a vast realm of icy bodies. Here, in the dim frontier, lies the Kuiper Belt, a broad ring of frozen remnants from the solar system's formation. Among these are several worlds large enough to be round, worlds that in another context might have been called planets. In fact, one of them was long honored as the 9th planet, Pluto. Today, we classify Pluto and similar bodies as dwarf planets, a category born from the realization that our cosmic neighborhood has more planets than we once thought, and that not all planets are equal in their orbital status. These distant dwarfs are small in size but rich in diversity, and they have forced us to confront the question, what does it truly mean to be a planet? Let us begin with Pluto, the iconic dwarf planet and former 9th planet. Discovered in 1930, Pluto orbits roughly 5.9 billion kilometers from the Sun on average, on a path that is highly inclined and elliptical. For 76 years, it was counted as the outermost planet, depicted as an icy oddball, until the early 21st century brought a paradigm shift. Pluto is about 2,377 kilometers in diameter, less than 20% of Earth's diameter, smaller than our Moon. But what it lacks in size, Pluto makes up for in personality. In 2015, NASA's New Horizons spacecraft flew past Pluto and revealed an astonishingly complex world. Far from a simple cratered ice ball, Pluto displays a mosaic of terrains: towering water, ice mountains rising 4,006 kilometers high, vast smooth plains of nitrogen ice with no craters, and dark reddish regions rich in organic molecules processed by sunlight. The most famous feature is Tombor Regio, nicknamed the heart of Pluto, a bright, heart-shaped area dominating one hemisphere. The left lobe of this heart, Sputnik Planitia, is a 1,000 km wide basin filled with nitrogen, carbon monoxide, and methane ices. This frozen plain is segmented into polygonal cells, evidence of convection. Pluto's interior heat causes the nitrogen ice to slowly overturn like a lava lamp, erasing craters and renewing the surface. It's a bit mind-boggling. Here is a tiny world at the solar system's edge, with active geology powered perhaps by the slow cooling of an internal ocean, or by exotic forms of heat transfer in the ice. Pluto's thin atmosphere is another surprise. When near perihelion, its surface ices sublimate, forming a tenuous atmosphere of nitrogen with a touch of methane. This atmosphere is about 100,000 times thinner than Earth's, but enough to form layers of delicate blue haze, as imaged by New Horizons when it looked back at Pluto, eclipsing the distant Sun. In Pluto's sky, the Sun is just a brilliant star, but it still drives a faint weather cycle. As Pluto recedes from the Sun, its atmosphere can partially freeze out onto the surface.
New Horizons saw that Pluto's skies are layered with haze up to 200 kilometers altitude, and that the atmosphere is slowly escaping to space, forming a tail like a comet's. Standing on Pluto, you'd see a dim daylight with a charcoal-colored landscape, low gravity, and if you looked up, a thin bluish glow around the horizon from the atmospheric haze. Pluto doesn't wander alone. It has a system of 5 moons. The largest, Charon, is so big that Pluto and Charon Co. orbit each other around a point in space between them. Charon itself is a fascinating world. New Horizons showed it has a rugged surface with a massive equatorial canyon system far longer and deeper than the Grand Canyon, and a strangely bi-colored complexion. The northern polar region of Charon is reddish, likely stained by gases that escaped Pluto and froze onto Charon, then were altered by solar radiation into reddish tholins. The mutual orbit of Pluto and Charon is tidally locked. Each keeps the same face toward the other, waltzing through space as an inseparable pair. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier and irregularly shaped, probably captured or coalesced debris from the giant impact that created the Pluto-Charon system billions of years ago. Moving outward, we find Eris, the troublemaker that precipitated Pluto's demotion. Eris was discovered in 2005 by a team led by Mike Brown. It's an object currently slightly smaller in diameter than Pluto, but more massive by about 25%. Eris orbits the Sun on a highly eccentric path. When found, Eris was hailed in the media as the 10th planet, but its existence underscored that Pluto was not unique. Astronomers suspected many Pluto-sized objects awaited discovery. Eris was named after the Greek goddess of discord, fitting for the chaos it introduced into our understanding. It has one known moon, Dysnomia. Eris's surface is extremely bright. Its great distance means Eris is in deep freeze. If it comes closer, it might develop a thin atmosphere like Pluto's that refreezes when far out. Eris's discovery forced the IAU to formalize the definition of planet, and under that definition, Eris joined Pluto as a dwarf planet. But in terms of geology and interest, Eris is very much a planet, like world, simply one of a vast collection in the Kuiper belt. Besides Pluto and Eris, the IAU has so far recognized 3 other dwarf planets: Ceres, Haumea, and Makemake. Ceres is unique as the only dwarf planet located in the inner solar system, residing in the asteroid belt between Mars and Jupiter. In fact, Ceres was the first dwarf planet discovered and initially considered a planet until many more asteroids were found. Ceres is about 940 kilometers in diameter, roughly the size of Texas, and contains about a third of the mass of the entire asteroid belt. NASA's Dawn orbiter visited Ceres in 2015 and unveiled a cratered world that, while much smaller than Pluto or Eris, still shows signs of internal complexity. Most famously, Dawn spotted mysterious bright spots on Ceres, particularly in the crater Ocata. These bright patches turned out to be deposits of salts left behind by briny water that erupted or seeped to the surface, essentially cryovolcanic salt flats. This indicates that Ceres, even at its modest size, had a subsurface reservoir of salty water or mud that occasionally breaches the surface as a kind of ice volcano. One such cryovolcano on Ceres is Ahuna Mons, a solitary mountain likely formed by the extrusion of viscous, icy material that then hardened. Ceres likely differentiated into a rocky core and icy mantle. It may even hold a remnant subsurface ocean or pockets of liquid. Though cold and airless, Ceres surprises us by being a kind of geological bridge between the rocky inner worlds and the icy outer worlds. Back to the Kuiper belt, Makemake is another dwarf planet, slightly smaller than Pluto. Discovered in 2005, Makemake orbits at about 45 AU on a mildly tilted orbit. It has a very high reflectivity as well, with a surface of methane and ethane ices that give it a red-brown color. For a long time,
Makemake was thought moonless, but in 2016, a tiny moon was found in Hubble images. Knowing its moon will allow us to determine Makemake's mass and density. Makemake has no known atmosphere, and its average surface temperature is around 240 degrees Celsius. Then there is Haumea, one of the strangest known dwarf planets. Discovered in 2004 and officially named in 2008 after the Hawaiian goddess of childbirth, Haumea is not spherical but rather ellipsoidal due to its incredibly rapid rotation. A day on Haumea is just under 4 hours. This fast spin elongated Haumea into a rugby ball shape. It's as if someone grabbed a ball of taffy and whirled it around. The centripetal force stretched it out. Haumea is also notable for its composition. It's largely water ice with a denser core, suggesting it might be the fragment of a larger body that collided and spun up. Supporting that, Haumea has 2 moons and is associated with a swarm of smaller Kuiper belt objects that share similar orbits and water-ice spectra, likely pieces of Haumea's shattered past self. In 2017, observers caught Haumea eclipsing a star and discovered it even has a ring, a 70-km wide ring of particles around its equator, likely in the plane of its fast rotation. Haumea's existence stretched our idea of a planet, showing that something can be round-ish and orbiting the Sun, yet far from symmetric or solitary. Beyond these, dozens of other objects around the size threshold for dwarf planet likely exist. Quaoar has a moon and possibly a ring of its own. Sedna lurks on an 11,000-year orbit that takes it out to nearly 1,000 AU, possibly the first known member of the inner Oort cloud. The more we look, the more we find a continuum of worlds bridging planets and comets. The dwarf planets collectively highlight the continuum of planetary sizes and the gradations in the solar system's architecture. They forced the question, where do we draw the line between planet and smaller bodies? The 2006 IAU definition drew that line based on orbital dominance. By that rule, Pluto, Eris, Haumea, Makemake, and Ceres were reclassified because they share their space with many peers, but that definition remains debated. Some planetary scientists prefer a geophysical definition. If it's round by self-gravity, call it a planet, which would make dwarf planets planet in a broader sense. Others note that even Earth hasn't entirely cleared its orbit, but Earth so overwhelmingly outweighs them that the spirit of the definition holds. The public often still refers to Pluto as a planet out of affection. In truth, terms like planet are human categories we impose on nature's spectrum. Whether we call Pluto a planet or not doesn't change Pluto itself, with its glaciers of nitrogen, atmosphere that snows out, and potential subsurface ocean. Pluto defies any notion of being a static asteroid. We've learned that these so-called dwarfs can be just as complex and geologically active as the big planets. They are worlds by any meaningful measure. The classification is mainly about how they fit into the solar system's structure. Pluto hasn't cleared its orbit because it lives in a bustling disk of other icy bodies. That tells us about where and how it formed, but it doesn't diminish its status as a fascinating world. Indeed, studying dwarf planets like Pluto and Ceres has yielded huge insights. Ceres taught us that even small bodies can differentiate and possibly harbor liquid water or mud under the surface. Pluto showed that even in the far frozen reaches, geology goes on. Exotic ices can flow and convect like glaciers, and cryovolcanoes can build mountains. These bodies are time capsules from the solar system's formation and laboratories for processes at the extremes. They and their ilk likely delivered volatiles to the larger planets. And when we consider planets around other stars, many might be more akin to these intermediate worlds than to the 8 major planets we started out with. Having completed our grand tour of the solar system, from the sun, scorched rocks, to the gas leviathans and distant ice dwarfs, we can step back and summarize. Our solar system contains a family of worlds with a common origin, but wildly divergent paths. Some went dry and airless, others drowned in thick atmospheres. Some stayed warm inside, churning and resurfacing, others went cold and quiet. And around at least one modest star out of billions, one small rocky planet found a perfect balance and became alive. With this perspective, we now venture beyond the solar system to the planets that orbit distant suns. Here, we will apply what we've learned to understand how we detect these alien worlds, what types we've discovered, and what that means for the potential for life in the cosmos. Beyond our solar system, the exoplanet revolution. For thousands of years, humans wondered if the stars in the night sky had their own planets. In the last few decades, we found the answer, a resounding yes. We are living through a revolution in which exoplanets, planets around other stars, have gone from speculation to a catalogue of thousands. This discovery has expanded our concept of what a planet can be and placed our solar system in a galactic context. The first discoveries were surprising. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed exoplanets, and they were orbiting a pulsar. These were likely bizarre worlds that survived a supernova or coalesced from its aftermath. Not at all what we expected for the first planets beyond our solar system. Then, in 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, 51 Pegasi b, a planet at least half the mass of Jupiter, but orbiting so close to its star that its year is only about 4 days. This was a hot Jupiter, a kind of planet unknown in our solar system. It forced us to realize that planetary systems can be very different from ours. Since then, a torrent of discoveries has followed. Astronomers detect exoplanets mainly by two methods: the radial velocity method, which measures the star's subtle wobble due to an orbiting planet's gravity, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it. The Kepler Space Telescope stared at 150,000 stars and measured their brightness precisely, catching thousands of tiny dips that revealed over 2,600 confirmed exoplanets. These planets range from larger than Jupiter gas giants to smaller than Earth worlds. We learned that super-Earths and mini-Neptunes are extremely common, yet our solar system has none of those, implying our setup might be somewhat unusual. We found hot Jupiters, gas giants hugging their stars in scorchingly tight orbits, and hot Neptunes and warm Saturns, and more. We found multi-planet systems packed in close to their stars, some with planets in orbital resonances. We found circumbinary planets, planets orbiting two stars. We found free, floating planets by gravitational microlensing, rogue worlds that drift through the galaxy untethered to any star. And we found planets in the habitable zones of their stars, at distances where, if conditions are right, liquid water could exist on a rocky surface. One of the most exciting sets of discoveries was the TRAPPIST system. 7 Earth-sized planets orbiting a dim red dwarf star only 39 light-years away. 3 of these lie in the star's habitable zone. They are all tidally locked and crammed in a space that would fit well within Mercury's orbit. This system provides a tantalizing example of a very different kind of solar system architecture, one where a tiny star can have a retinue of Earth-size worlds potentially capable of retaining atmospheres. What are their surfaces like? Could any have water or life? Future telescopes like the James Webb Space Telescope are actually beginning to probe their atmospheres by analyzing starlight that filters through during transits. Exoplanets have shown us an astounding diversity of types. Hot Jupiters, gas giants orbiting extremely close to their stars. These have atmospheric temperatures of 1,000 pounds and 2,500 excites or more. Their atmospheres are puffed up by heat. Some are losing gas under the stellar radiation. They challenged our formation models. How did such big planets get there? We think they formed farther out and then migrated inward due to interactions with the protoplanetary disk or other planets. They taught us that migration can be a common process. Super-Earths. Planets a bit larger in radius or mass than Earth. Some may be rocky, others may have thick atmospheres. They might actually span a spectrum from big rocky planets to small gas planets. Not having one in our system means we had a gap in our understanding. Now we see they might be one of the most common types in the galaxy. A super-Earth might have higher gravity and retain a thick atmosphere or oceans for billions of years. Could they be even more clement for life than Earth? Or could they all turn into gas dwarfs with puffy atmospheres that make them uninhabitable? We're trying to find out by measuring their densities. Some super-Earths like 55 Cancri E are very dense, whereas others like Kepler 38d appear to have low density. Ice giants and sub-Neptunes. Many systems have planets in the 2 through 4 Earth radii range, akin to scaled down versions of Neptune and Uranus. These might have thick hydrogen, helium atmospheres on a rocky/icy core. Some could be more water-rich. The line between super-Earth and sub-Neptune might be around 1.6 thousand Earth radii. Intriguingly, Kepler data showed a dip in planet frequency around that size, suggesting many planets either have significant gas envelopes or have almost none. This phenomenon, the radius gap, likely reflects how planets either stop growing early and stay rocky or accumulate enough gas to puff up. The borderline worlds might have lost some atmosphere due to stellar radiation, ending up as rocky cores. Gas giants. Plenty of Jupiter, like or Saturn, like exoplanets have been found at various distances, some close, some at Earth, like distances, some far out. A few even orbit at Jupiter, like distances from Sun, like stars, implying their systems might have distant architectures vaguely resembling ours. We found giants in eccentric orbits. Some gas giants orbit binary star systems. We've even directly imaged a few young gas giants at wide separations. Rogue planets. Gravitational microlensing surveys have hinted that there may be numerous free-floating planets, perhaps ejected from forming systems or formed in isolation. Some estimates suggested they could be as numerous as stars or more, though recent data suggests not that common for Jupiter mass ones. Still, it implies planet formation can be a turbulent process, with some worlds flung into the galaxy to wander alone. These would have no sunlight, just faint glow from leftover heat or radioactivity. A larger rogue could retain a thick atmosphere and maybe an internal ocean kept liquid by radiogenic heat or tidal heating from a prior moon, but life on such worlds would be a stretch. Exotic worlds. Some planets are simply weird, like lava worlds such as Corot 7b or Kepler 10b. Rocky planets so close to their stars that their surfaces are likely molten on the dayside, with rock vapor atmospheres and mineral clouds that rain pebbles. Or ocean worlds that might be nearly all water by mass, essentially giant versions of Europa or Enceladus that grew larger. There's the idea of carbon planets around stars with different compositions, perhaps worlds where graphite and diamonds are abundant, or surfaces of carbide rock under tar, like skies. There are also puffy planets, gas giants with anomalously large radii for their mass, like WASP 17b, which is about half Jupiter's mass, but 1.7 times its size, and planets orbiting pulsars, or extremely metal, poor stars, or white dwarfs, each situation leading to unusual characteristics. When we compare these exoplanets to our solar system, we see that our system might not be typical in some respects. The absence of a super-Earth in our solar system is a puzzle. Perhaps Jupiter's formation prevented one from coalescing by scattering material. The lack of hot Jupiters in our system is a blessing for us. It appears that giant planets that migrate can disrupt inner systems heavily, whereas ones that stay put allow inner rocky planets to remain. Our relatively circular orbits and spaced-out configuration might not be the most common outcome. Many stars have multiple super-Earths in orbits closer than Mercury's, for example. Yet, among Sun-like stars specifically, some analyses suggest systems with a giant planet at Jupiter, like distance and small inner rocky planets, could be not extremely rare either. We're still trying to figure out how special our arrangement is. The significance of discovering exoplanets is profound. We now know that planet formation is a natural part of star formation. Planets are everywhere. The galaxy likely holds tens of billions of potentially habitable rocky worlds. We've taken the concept of planet from 5 wanderers in the sky to a cosmic norm. And each type of planet we find tests our theories. How do hot Jupiters form? Likely through disk migration or interactions. Why are super-Earths so common? Perhaps many systems form multiple mid-sized cores, which either become super-Earths or mini Neptunes, depending on how much gas they capture and how fast they migrate. What about Earth-like planets? Statistical studies from Kepler suggest perhaps 20–25% of Sun-like stars have an Earth-sized planet in the habitable zone. Around red dwarfs, potentially an even larger fraction have Earth-sized planets in the habitable zone, as seen with TRAPPIST and others. However, red dwarfs are volatile. Their flares and long-lived activity might strip or sterilize those planets' atmospheres. The search is now shifting from finding exoplanets to characterizing them, measuring their masses and radii, detecting their atmospheres via spectroscopy, and even directly imaging some. We have detected atmospheric constituents on some exoplanets, sodium in hot Jupiter atmospheres, water vapor on some, even hints of things like titanium oxide, or possibly clouds of silicates or iron. In 2019, water vapor was detected in the atmosphere of a Neptune in its star's habitable zone, raising interest. The ultimate goal is to detect biosignatures, signs of life, in an exoplanet's atmosphere, such as oxygen or methane out of equilibrium, or other peculiar combinations that strongly suggest biology. That will require the next generation of telescopes and perhaps specialized space observatories with coronagraphs or star shades to directly see Earth, like planets next to their bright stars. The types of exoplanets we've discovered inform our quest for life. We've learned that terrestrial planets often come in families. A star might have several, some perhaps larger or smaller than Earth. We've seen that habitable zones around red dwarfs can host multiple tidally locked Earth-size worlds. Whether those can support life is an open question. Tidal locking means one side is always hot, the other cold. But if they have atmospheres or oceans, they could redistribute heat. We also consider how giant planets in a system might affect habitability. A Jupiter analog could help by diverting comets or hinder by destabilizing orbits. Our solar system's giant planets likely had a hand in delivering water, and also in preventing too many super-Earths from forming in the inner regions. In the context of habitability, the solar system offers 3 main candidates for life as we know it: Earth, Mars, and ocean moons. But none besides Earth have confirmed life. So as we look outward, we refine what conditions might be needed. Liquid water, certainly, is high on the list. A source of energy is needed. A stable environment over some billions of years might be necessary for complex life. Planets in the habitable zone of Sun, like stars, might be best situated for that. Red dwarf habitable zone planets get a lot of flares, especially in youth. Could life survive that? Possibly, if under ocean or ground, or protected by a magnetic field and thick atmosphere. We remain cautious but hopeful. The future exploration of exoplanets is accelerating. The James Webb Space Telescope is already peering into some transiting planets' atmospheres with unprecedented detail. Upcoming missions like the Nancy Grace Roman Space Telescope will use microlensing to find rogue planets and cold planets further from stars, and test technologies for direct imaging. Further down the line, proposals for missions like LUVOIR or HABEX specifically aim to directly image Earth like planets around Sun, like stars, and search their spectra for biosignatures. On the ground, extremely large telescopes coming online in the late 2020s will be able to probe smaller exoplanets and perhaps take crude spectra of super-Earth atmospheres. It's conceivable that in the coming decades we might identify a planet where life could exist, or even find hints that it does exist, such as an atmosphere out of chemical equilibrium, strongly suggestive of biological activity. As our gaze extends to the stars, we carry the lessons of our solar system with us. We now know Earth is not alone as a potentially habitable world. There may be billions of Earths in our galaxy, but we also know habitability is fragile. Climate catastrophes like what befell Venus and Mars remind us that a planet's fate can change drastically. Earth has been lucky, but we must keep it that way.
Life among the stars, the quest for habitability. When we talk about habitability, we usually mean conditions suitable for liquid water and life as we know it. From our study of planets, we've identified key factors. Distance from star. The concept of the habitable zone is crucial. Not too hot, not too cold for liquid water on the surface. For our Sun, that roughly spans from just beyond Venus's orbit to just beyond Mars's. For smaller, cooler stars, the habitable zone is much closer in. For bigger, hotter stars, it's farther out, but those stars live shorter lives.
Atmosphere. A planet needs an atmosphere thick enough to create pressure for liquid water and to circulate heat, but not so thick as to induce a runaway greenhouse. Too thin, and water either freezes or boils away. The composition matters too. CO2 provides warmth, but too much can cook a planet. Some gases can be toxic to life. On Earth, life itself altered the atmosphere, creating the oxygen we breathe, which in turn allowed complex life.
Magnetic field. As we discussed, a magnetic field can protect a planet's atmosphere from stellar winds. Earth's field likely helped us maintain our water and air over geologic time. Mars lost its field early, and then its atmosphere eroded away largely. Venus lacks a field, but its atmosphere is so thick that even with losses, it remains dense. Around active stars, a magnetic field could be even more critical to buffer the planet from high-energy radiation and flares. Internal heat and geology. Plate tectonics appears to help regulate climate via the carbon cycle on Earth. Volcanism also releases trapped gases and replenishes the atmosphere. A geologically dead planet might end up like the Moon. No atmosphere, cold interior, and static surface, not hospitable. Mars's waning volcanism might have doomed its climate. Venus's rampant volcanism may have contributed to its runaway greenhouse by belching massive CO2. A balance of geological activity is likely beneficial, enough to drive cycles and field generation, not so much as to create continuous global volcanism that might make a world too volatile for stable ecosystems. Stable climate and star output. A planet needs time for life to evolve. Earth has had liquid water for almost 4 billion years through various climate swings. A star's output can change. Earth's biosphere and geology compensated, keeping the planet habitable. If the changes were more extreme, or Earth's feedbacks weaker, life might have been snuffed out. So habitability is a combination of initial conditions and subsequent luck and balancing feedbacks. When we look at exoplanets, especially those in habitable zones, we assess these factors. Does the planet likely have an atmosphere? What's the star like? We've identified some promising, potentially habitable exoplanets. Proxima Centauri, B. TRAPPIST, E, F, G, as mentioned. Earth-sized, in or near habitable zone around a dim star. Kepler, 452b, around a Sun-like star, often touted as older cousin of Earth, is larger, and the star is 6 billion years old. Interesting if it's rocky, but we're not sure it isn't too massive, having a thick atmosphere. Kepler, 2F and Kepler, 186 if, are smaller planets in their stars' habitable zones, though their stars are a bit cooler than the Sun. Many others have been found by Kepler and TESS,
that are unconfirmed or with limited information. Ultimately, detecting life is the holy grail. What might be a sign of life? On Earth, the combination of abundant oxygen and methane is a strong biosignature. Seeing both would raise eyebrows. Also, things like the spectral edge of chlorophyll could be a signature if we ever got a direct color spectrum of an exoplanet's surface. Even seasonal changes in atmospheric composition could hint at biology. It's tricky because we have only one example of life's impact on a planet, Earth, and alien life might produce different gases. Also, non-biological processes can sometimes mimic biosignatures. So context is everything. We'd need to understand the planet's star, history, and environment to interpret signals, while the exoplanet hunt proceeds mostly via remote sensing. In our own solar system, we can go to these worlds to search for life or conditions. Mars is currently being combed by rovers and orbiters. Europa and Enceladus are top targets. Europa Clipper will orbit Jupiter and repeatedly fly by Europa to map its ice and composition, even scouting for plumes to sample for organic molecules. JUICE will explore Jupiter's moons and eventually orbit Ganymede, studying its ocean and magnetic field. For Enceladus, a future mission concept aims to directly sample its geysers for biomolecules and maybe even signs of microbial life. Titan will be visited by Dragonfly, a flying drone like Lander that will hop across Titan's dunescapes to drill into organics and look for prebiotic chemistry or even life's handiwork. Thus, our exploration strategy is twofold. Within our solar system, investigate all potentially habitable niches. Beyond our solar system, improve our telescopes to identify promising Earth, like planets around nearby stars, and eventually directly image them. We stand at a moment in history where we can, for the first time, meaningfully search for life beyond Earth. Not long ago, planets around other stars was still hypothetical. Now it's routine science. The next leap, finding evidence of life's effects on another world, would be profound. It would tell us whether life is a cosmic common occurrence or a rare fluke. Either answer is deeply significant. If common, the universe may be teeming with biology and perhaps intelligence. If rare, then our pale blue dot is an even more precious oasis in a vast, perhaps mostly sterile desert. Future frontiers, exploring new worlds, and the fate of our planetary journey. What does the future hold for planet exploration? Both in continuing to explore our solar system and in reaching for others, the coming decades promise to be exciting. Within the solar system, several ambitious missions are on the horizon or in progress. We mentioned Europa Clipper and Dragonfly. These will illuminate the potential habitability of ocean worlds. Mars exploration continues. After Perseverance collects samples, a multi-part Mars sample return mission by NASA ESA aims to bring those samples to Earth by the mid-2030s, allowing labs on Earth to scrutinize Martian soil for signs of ancient life with far greater precision than any rover could. Plans for human missions to Mars loom on the multi-decade timescale. The 2030s or 2040s may see the first footsteps on Mars, fulfilling a dream long imagined. Humans could conduct science on Mars that robots struggle with, though robots will likely have already answered the life question by then. At Jupiter and Saturn, the next generation might be missions to actually land or sail in the oceans of the moons. A concept being studied is a Europa lander to drill through a thinner part of the ice, or a penetrator that melts its way down. Even more fanciful is a submarine for Titan's methane seas or an Enceladus ice drilling lander. These are technologically challenging, but so was landing humans on the moon. It's a matter of will and priority. There's also renewed interest in Venus. After decades focusing on Mars, NASA and ESA have recently approved missions to Venus in the 2030s, Da Vinci Plus and Veritas. ESA's Envision orbiter is planned as well. These missions will give Venus a fresh look, important for understanding how Earth, like planets, diverge. If Venus was once more temperate, when and how did it turn so hostile?
we might find clues of past water or ongoing volcanic gases. Farther out, Uranus and Neptune remain the only major planets not revisited since Voyager. The US Planetary Science Decadal Survey has prioritized a Uranus orbiter and probe mission for the 2030s. This mission would journey for around 15 years to Uranus, deploy an atmospheric entry probe to sample Uranus's air directly, and orbit Uranus for a few years to study its rings, magnetosphere, and moons. Such a mission would be a bonanza of science. Understanding ice giants will fill a gap in our knowledge of planet formation. After Uranus, Neptune is a logical next target, potentially in the 2040s, possibly with a Triton lander or ocean finder included. These missions, though far off, underscore humanity's commitment to exploring all corners of our solar neighborhood. In the realm of exoplanets, as discussed, new space telescopes like JWST are opening windows. JWST has already begun examining atmospheres of some transiting exoplanets and even directly imaged a couple of gas giants. Over its lifetime, it might be able to probe some super-Earth atmospheres around nearer stars for molecules like water or CO2. The Roman telescope will find many cold exoplanets via microlensing and carry a technology demonstrator coronagraph to directly image a handful of known giant exoplanets, sharpening our skills. By the 2030s or 2040s, we hope to launch a large segmented mirror telescope. Such a telescope, armed with a coronagraph or a starshade, could directly see Earth-sized planets around perhaps dozens of nearby sun, like stars, and take spectra of them, searching for biosignature gases. Imagine seeing a pale blue dot in the sky of another star and detecting, say, oxygen, or even a color variation due to continents and oceans. That would be a civilization, changing discovery. We stand perhaps a generation away from that possibility. There are also imaginative projects like Breakthrough Starshot, which envisions sending gram-sized microprobes to Alpha Centauri using powerful laser sails, reaching 20% the speed of light to get there in about 20 years. While highly experimental, if such technology matured, we could potentially have flyby images of planets around the nearest stars within our lifetimes, perhaps revealing continents or clouds on an alien Earth. It sounds like sci-fi, but no more so than Jules Verne's moon rockets did in the 1860s. Human curiosity drives innovation, and the payoff, touching another star system, would be historic. As we explore, we also reflect. All these worlds we visited in our minds, from Mercury's battered ground to Neptune's windy blues, have taught us about diversity and commonality. Diversity in that each planet is its own world with unique quirks. Commonality in that they are all part of one grand physical system, obeying the same gravity and chemistry, following similar stages of formation and evolution with variations on the theme. We've seen parallels, volcanoes on Earth and Io, sand dunes on Mars and Titan, polar lights on Earth and Jupiter, ice crusts on Europa, and our own Arctic Ocean. We've seen cautionary tales, a planet almost our twin that became a furnace, a small world that lost its shield and dried out. We look back at Earth with new appreciation for its perfectly tuned conditions, not too hot like Venus, not too cold like early Mars, big enough to hold air, spinning fast enough to have a magnetic field, blanketed by life that in turn helps maintain stability. The study of planets has also put us in our place. Copernicus removed Earth from the center. Galileo showed Earth is just one of many bodies. The last century revealed that even the sun is one of billions, and now that planets abound everywhere, our home is just one island in a vast archipelago of worlds. And yet, to us, it's special, the only known cradle of life. As we search for life elsewhere, we can't help but wonder about the rarity or ubiquity of life. Will we find biosignatures on Mars or Enceladus, or an exoplanet? If we do,
It means life might sprout wherever conditions allow, implying a living cosmos with many neighbors. If we don't, it could mean life is a freak accident, a cosmic miracle unique to Earth. In that case, the responsibility on us as stewards of the only garden of life increases immeasurably. Either way, studying planets has given us a cosmic perspective. Carl Sagan's famous pale blue dot speech encapsulated it. All of human history played out on a mote of dust suspended in a sunbeam. Every planet we visit reminds us of the fragility of habitability, how thin an atmosphere is, how delicate a balanced climate can be. We see Venus and fear a runaway greenhouse. We see Mars and fear the loss of a magnetic field and atmosphere. We turn those lessons to our own situation, recognizing our planet's climate is not static, that pumping greenhouse gases can push Earth toward a new, possibly unfavorable state. The barren surfaces of Venus and Mars urge us to be careful lest Earth follow their paths in some distant future by our own doing. Planets also teach resilience and change. Earth has gone through mass extinctions and recovered. Life has a tenacity. Who knows, maybe life exists in some form under the ice of Europa or in Titan's chemical stew, very different from Earth's biology. If we find even a second Genesis in our solar system, it means life is a cosmic imperative. If we don't find it nearby, we'll keep looking outward. Ultimately, the exploration of planets is a human story of curiosity, wonder, and reflection. We have gone from gazing at wandering stars to sending robot emissaries across the void to stand on those worlds and report back. With each step, we've been awed. We felt the volcanic heat of Io and shivered in the methane rain of Titan. We marveled at Saturn's rings, countless icy particles orchestrated by gravity into one of nature's most gorgeous sights. We flew through a geyser on Enceladus and tasted primordial water. We watched a sunset on Mars through the eyes of rovers, its sky tinged butterscotch by fine dust. These experiences, albeit through our mechanical proxies, have enriched our soul and expanded our imagination of what worlds are out there. Looking up at the night sky now, we no longer see just pinpoints of light. We see other suns with their own planets, perhaps a giant with storms bigger than Earth, or a warm ocean world enveloped in clouds, or a rocky orb struggling to hold on to an atmosphere. We might even see lights of another civilization, though none have been detected yet. The possibility is there, made real by the sheer number of planets. So we end our journey where we began, under the stars. But now, when we point out the wanderers, our neighboring planets, we do so with understanding and kinship. The word planet means wanderer, but ironically, planets also taught us how connected everything is. Wanderers though they are, they orbit in a family, influencing each other and their star. And we, wanderers ourselves, have begun to venture from our home to visit them, first with our eyes, then with our ships, someday perhaps in person. The story of planets is the story of cosmic islands and the voyages between them. It's a tale of creation, how dust can clump and ignite and then leave residue that becomes worlds both barren and lush. It's a tale of destruction and renewal, giant impacts that can destroy worlds or birth moons, atmospheres that can collapse or run wild, but also life that can emerge and transform a whole planet. It's a story that forces us to ask, how common is a world like ours? How rare are we? And where do we go from here? In the next decades, we may finally get an answer to, are we alone? By detecting life signs elsewhere. Or we may find that Earth is singular so far. In either case, planet exploration will continue, driven by the deepest human urges to know and to go. Unmanned or manned, we will likely set foot on Mars, dive into the seas of Europa with submersibles, maybe float in the atmosphere of Titan or Venus in balloons. We will refine our techniques to image Earth like exoplanets. Perhaps one day, far in the future,
our descendants will build starships to visit neighboring systems, turning those points of light into landscapes beneath their boots. As our perspective broadens, our appreciation of Earth deepens. The pale blue dot that Sagan spoke of is our only home in a vast cosmos, at least for now. The other planets show starkly that Earth's hospitality is unique in our solar system. So exploring other planets is not just about them, but also about us, holding a mirror to Earth. We see what happens when greenhouse gases go unchecked, or when a small planet cools and dries, or how a protective magnetic field can preserve a world. These lessons are invaluable as we manage Earth's future. Finally, there is an almost spiritual aspect. By understanding planets, we come to understand our place in the universe. No longer are we the center, we are part of something vast and magnificent. The diversity of worlds out there suggests that if life could arise here, it could arise elsewhere. And if it hasn't elsewhere, then we carry an enormous responsibility as the sole known bearers of consciousness to care for our oasis and perhaps spread life beyond it. We began this journey with the ancient wanderers in the sky. Now, having explored the fire of the inner planets, the grandeur of the giants, the ice of the dwarfs, and even peered to the worlds of other stars, we end with a renewed sense of wonder. The night sky will never look the same. Each dot is a sun, many with planets, some perhaps with beings looking back at a tiny sun pinprick that is our home. The voyage of planetary exploration has really just begun. There are new horizons to reach, literally, as with the probe New Horizons at Pluto, and profound questions still to answer. But one thing is certain, our curiosity will not cease. We will continue to wander, in person or by proxy, mind and body, outward to the planets and beyond. For in seeking these other worlds, we ultimately seek to know ourselves and our place in the cosmos. It is a grand story, one that spans from the fires of creation to the potential spark of life, and it's a story with no end in sight. Each planet we visited, by telescope or spacecraft, has left us changed. They have shown us beauty beyond measure, forces beyond fear, and resilience beyond expectation. In their extremes we find meaning. Mercury's day, night cycle, whispering that too much heat and too little air yields desolation. Venus's clouds warning how quickly paradise can be lost. Mars's dry rivers reminding that climate can turn on a planet. Jupiter's storms humbling us with their power. Saturn's rings teaching the elegance of gravity's order. Uranus and Neptune revealing that even on the edge of darkness, winds still dance. Pluto and its kin proving that even small worlds can be geologically alive. As we continue to learn, we should also take a moment to feel the awe. We are fortunate to live in a time when the long-lost siblings of Earth have been revealed in all their glory. A human from just 100 years ago could only dream of what we've seen. And a human 100 years from now might walk on Mars or float in a Europa submersible, living our present dreams. Our quest for knowledge and exploration binds the generations in a common continuum of discovery. So, step outside on a clear night. Find Venus blazing in the west or Jupiter rising in the east. Know that you're looking at entire worlds, places that we've now touched with our robotic emissaries and, one day, might touch with our hands. The sky that was once the realm of gods and myth is now open to us as a realm of nature to explore. The wanderers are no longer distant mysteries. They are destinations. They have become real places with landscapes and weather and histories we can narrate. And in exploring them, we've woven their stories into our own. We too are wanderers. As Sagan said, we began as wanderers, and we are wanderers still. We have lingered long on the shores of the cosmic ocean, but now we are setting sail among the stars. In the end, the study of planets teaches us humility and unity. All those worlds out there, and here we are,
one small crew on spaceship Earth, sailing together through space and time. The pale lights of Mercury, Venus, Mars, Jupiter, and Saturn in our sky are like signposts, telling us where we've been and where we will go. When we finally decipher the secrets of alien atmospheres or find microbes on a distant moon, it will underscore that we are a part of this universe, connected to the planets and stars around us. We are not apart from nature. We are born of the same processes that birthed the planets. The voyage will continue. New rockets, new telescopes, new generations of scientists and explorers will carry the torch. They'll answer questions we haven't thought to ask, and surely encounter surprises we haven't imagined. Planets will continue to fill us with wonder, whether it's weird new exoplanet types or hidden oceans discovered under icy crusts. Each answer will likely raise more questions, as is the way of science. But that is a joy, not a frustration. It means the adventure of discovery is endless. There will always be another horizon, another world to learn from. And as long as humans have eyes to the sky and minds that dream, we will be out there, exploring, moving outward, one world at a time, forging connections across the darkness. In a sense, by exploring the planets, we are the universe exploring itself. Matter that became life, life that became intelligent, now reaching back out to understand the grand mechanism that produced us. Every footprint left on the moon, every photon counted from a distant exoplanet, is the cosmos coming to know itself through us. Our journey through the planets has thus been a journey inward as well, into the nature of who we are and what we may become. When future explorers stand on Mars and look up at a sky with 2 moons, or when a robotic probe sends back the first images from an Earth, like planet light years away, the sense of connection will only grow stronger. We'll realize ever more that we share the universe with all these worlds, and maybe share it with other life. For now, we cherish our pale blue dot while reaching for others. We end our tour back on Earth, gazing up, but with new eyes. The wanderers in the sky are no longer distant gods, but places we know. Siblings in the solar family, each unique, all kin. We have walked among them in our imaginations and through our proxies. Soon, we will with our own feet. The story of planets is ultimately a celebration of human curiosity. We dared to ask ancient lights what they were, and we answered, revealing a universe richer than our ancestors could have believed. Stand under the night sky and feel that connection, tiny though we are. We understand those points of light now. Mercury, Venus, Mars, Jupiter, Saturn. We know them intimately. And far beyond, around myriad stars, countless other planets circle, waiting for our discovery. The wanderers will guide us outward, and wherever we go, we will carry the legacy of understanding forged here at home. In that sense, the journey of exploring planets is a journey of self-discovery for humanity. We set out to find new worlds, and in the process, we found ourselves, one people on one world, learning that the cosmos is full of worlds. It is perhaps the grandest revelation of all. The planets have taught us that the only borders are those we create ourselves. In the cosmos, all worlds share the same sky. The wanderers still move across the heavens as they did for the ancients. But now, when we see them, we greet them as familiar friends, places we've been or soon will go. And as we trace their paths and even send our emissaries to dance among them, we too become wanderers beyond the earth, united in the eternal quest to know the universe and our place within it. The story of planets, our story, continues, onward and outward, under the cosmic sky that we all share.